Where the heck? I can't. Okay. No. Sorry. It looks like I'm a problem sharing here. It shows my total computer screen, I suspect, right? Let me see what's happening here. Let me stop sharing and try again. PowerPoint. I can see my Windows. Let's see what we have. Oh, here we go. Finally. Something different from the usual stuff. All right. I hope you see the slides. Let me go full screen. Okay. So today I'd like to review a little bit what we did last time. It was tough going, I suspect. So don't feel bad if you missed a few steps, so to speak. So trying to go from the quantum formulation of transport in terms of the density matrix, so the Liouville-van Neumann equation, trying to go to the Boltzmann equation. I didn't use the word derive because it cannot be derived, as I said last time, and we'll see it again today. And then I'm not sure if we'll get to that today. I hope so. Start dealing with, once we have the Boltzmann transport equation, and we will see what are the major assumptions or approximations that we have to make to go from the quantum transport to the semi-classical picture. How do we solve it? So this is something that could be the subject of an entire course. There are so many ways one can solve the Boltzmann transport equation. It's a tough equation to solve. As far as I know, mathematicians have not yet performed the first step, which is showing that a solution exists and it's unique, except for some very special cases. It's a partial differential equation, it's integral, and it can be nonlinear. So it's a tough mathematical object. And there is a wealth of methods which have been developed since probably the late 1940s, dealing with the Boltzmann equation for electron transport. Of course, things started off earlier because the Boltzmann transport equation goes back to when Boltzmann formulated, so the late part of the 19th century. So this will be something that will require a little bit of time. So eventually, I would like to conclude the course. I think we have, in addition to today's lecture, 3 more lectures, to talk a little bit about something which is of present importance, which is transport in low dimensionality materials, going back to inversion layers, which are more, I could say, mundane, quantum wells, and particularly today there's a lot of interest in 2-dimensional materials and other 1-dimensional structures like quantum wires, carbon nanotubes. So a little bit about this. Before going there, though, I'd like to mention briefly the formulation of the quantum transport equation, not necessarily starting from where we started, which is the density matrix, but from the Green's functions method, give a very broad overview of various techniques which have been used, and then some numerical method to solve them, and then show some results. And this will conclude the class. I think that the last lecture will be mostly a review. I'll try and make it clear what kind of questions will be asked in exam, what kind of knowledge I will require. Not everything I said in class, as I mentioned many times, there will be subjects which are a little bit too advanced. Okay, so let's go back. So last time we saw the first steps in our plan to go from Liouville-van Neumann to the Boltzmann equation. So the idea is, to repeat, we start with a system, which is, think of some device with 2 contacts and applied bias between source and drain or emitter, collector, whatever. You consider this system. the system is connected to the external world, to reservoirs, particle reservoirs, and to a thermal bath. So we're considering interactions of electrons with phonons. The idea that we will use is to open one contact, inject some electrons, say from the source. They will be injected according to the Fermi-Dirac equilibrium distribution of the contact. They get in the device instantaneously. We close the system. So now we have a closed system, which is interacting with a thermal bath, so energetically open, but particle-wise, it is closed, no exchange of particles with the environment. We look at how the system approaches equilibrium by starting from the equation of motion for the density matrix, which is the Liouville-von Neumann equation. We will proceed integrating it formally for the first step, stopping at the leading order in terms of the interactions of the electrons with the external bath. The density matrix will be expressed on a basis of functions which are the eigenstates of the unperturbed Hamiltonian that contains not only the kinetic energy of the electrons, but also the potential, the external potential that we have applied, but not the interaction with the phonons that will be considered as a perturbation. We proceed by using the argument that Van Hove gave. As I told you last time, the master equation, which is the form of the collisional operator we want to deal, was first obtained by Pauli in the early 30s, but it required the approximation of a phase randomization at every time step. Van Hove showed that this is not necessary for some particular classes, I should say, two classes that he has identified of initial states. We'll find how the system evolves in equilibrium with the master's equation. It will take a little bit of work to derive it. Finally, we will open the device, adding a term which expresses the interaction, the exchange, I should say, the exchange of particles between the closed device and the contact. So the system now will become open. We will take the Van Hove limit, which is the crucial step, which is responsible for introducing irreversibility or breaking the time reversal symmetry of the system. And this will be the tricky step. As I said last time, it's a little bit disappointing that it boils down to a mathematical trick to regularize an integral. Physically, it's equivalent to the step that we make in deriving Fermi golden rule, when we go from finite times, a finite duration of the collision, to a completed collision, which is when we take the limit of time going to infinity and we obtain the delta function expressing energy conservation. So this is the crucial step, which is what amounts to semi-classical, the molecular chaos or the Stoss-Allen-Satz approach, the approximation that Boltzmann used semi-classically. Having formulated this, we will find that the collisional operator has a form of a master type, expressing simply exchange of occupation among states according to some scattering processes which are instantaneous, local, and do not have any memory of the past history of the particles, of the states of the system, which is indeed what introduces irreversibility. And then we consider now a large device. This will be true for a small device in which we can assume that the initial state can be expressed essentially by a superposition of plane waves, one of the two classes of initial states that Van Hove identified as leading to the master equation. So we'll consider a large device in which this approach is not correct and making some assumption. We will slice the device into several sections, each section small enough to have a collisional operator of the master type, and then we'll stitch together the slices, making some assumption about incoherence between transport among various slices, or I should say between adjacent slices. And this will lead us to the Boltzmann equation. So it's a long process. I gave you some ideas about the main argument that Leon Van Hove gave, which is crucial. Again, this is a very tough paper that was published in 1955, but it contains one of the most comprehensive approach to, how could I say, explaining the onset of irreversibility. It's not a formal proof. There are some assumptions. As I said, the H theorem, which is the ultimate goal that Boltzmann had in mind, as far as I know, remains unproven. Or as I should say, as I said last time, it has been proven in many different ways, so that probably we can say that there is no definite proof. Also because irreversibility means something different to different people, depending on whether you look at from a thermodynamics point of view, statistical mechanics. I brought the example of cosmology, in which there is no external observer, and things get very complicated there. So the idea is to start from this system. We assume that this system is originally off equilibrium. We use as basis functions for our states the eigenvalues of the unperturbed Hamiltonian. And the unperturbed Hamiltonian will be the electron Hamiltonian, given by some kinetic energy operator, view as the usual kinetic energy term for parabolic bands, if you wish, or free electrons, and an external potential. So the external potential for now will be assumed to have been already diagonalized, fully diagonalized, and the states that we have are eigenstates of this electron Hamiltonian, which we consider unperturbed even if there is an external potential. Then we have a phonon Hamiltonian we can treat as we did in the past, and then there is the perturbation term, which is the electron-phonon coupling. So the phonon Hamiltonian has the usual expression of a sum over a collection of harmonic oscillators, each labeled by a branch index eta, longitudinal, transverse, optical, acoustic, whatever you wish over here, and a Q vector. And this labels our phonons. And the electron-phonon Hamiltonian, which is our perturbation term, can be written in usual terms expressing this term, which amounts to destroying an electron in a state I, creating an electron in a state J. So this expresses a transition from a state I to J. I should stress that I and J are labels of these eigenstates of our unperturbed Hamiltonian, and this is a set of indices in principle. If there is no external potential, I and J actually will be the wave vectors or plane waves, but in general will be a set of many indices. In 3 dimensions, there will be 3 indices or 3 labels corresponding to the 3-dimensional space. Eventually, you may even consider spin is already included into these generalized indices. These are the creation and annihilation operators of phonon. So this is a phonon emission process. This is a phonon absorption process because we destroy a phonon. And this is some coupling constant, which is the same coupling constant that we saw before, dealing with the electron-phonon interaction, except that now we express it on the basis of this function. So these will be the matrix elements between these eigenstates of the Hamiltonian. This will be the usual k and k plus q, if you wish, if we're dealing with plane waves. In general, these will be different wave functions, depending on what is our potential in the system. So we start with a system which for now it's open for a short while. One contact injects these electrons in a situation of off equilibrium. If you don't want to open the system, you may think of having excited many carriers optically or by giving a shot of high temperature so that the system is driven off equilibrium, and then we'll see how it decays, and that's our goal. I've extracted formally a coupling constant alpha in front of the electron-phonon interaction. There will be some dimensionless coupling constant so that we can formalize an expansion in series or perturbation series on this coupling constant. We assume that at the beginning, both the electrons and the phonons are at thermal equilibrium, and we will be considering not the entire density matrix, but what we call the reduced density matrix, which is essentially considering the full density matrix, but taking the trace over the phonons, which is this process. In quantum statistical mechanics, this is sometimes called taking the trace of the irrelevant degrees of freedom. And we will assume that the phonons are always at thermal equilibrium. It's an assumption, and you may think that that's a way that we introduce irreversibility. Actually not. we'll see that we do not. We will still obtain, even with this assumption, obtain a reversible equation of motion for the density, the reduced density matrix. And that's because from the onset, we do not put any information about the phonon dynamics. So they always stay at thermal equilibrium. So if you want to play the movie forwards or backwards, makes no difference. So it's an assumption, it's a strong assumption, which particularly today when power dissipation in electronic circuits is a major issue, it's an oversimplification, but if we didn't take this assumption, we would have been forced to deal with the time evolution of the phonon density matrix. We would have to consider anharmonic interactions, phonon transport. So let's keep things simple and assume that the phonons are at thermal equilibrium. So we'll consider this object, which is the trace over all the phonons of this operator. This operator, you may recognize it as the number or the density of electrons in a state ij. The diagonal term, C dagger I, Ci, is just the number of, so the occupation of the state I of our unperturbed Hamiltonian. And as we discussed last time, the density matrix has additional information compared to the distribution function that we may have in classical statistical mechanics, because we have off-diagonal terms that represent the amplitude that the system may be in a linear superposition of two different states, I different from J. This is something that clearly doesn't exist in classical mechanics. So that's why we need a matrix and not a simple distribution function. So this will be the main object that we want to study. We start from the Liouville-von Neumann equation of motion for the density matrix. This superscript I, if I remind you, is implies that the picture that we use in the interaction picture, in which states evolve according to the perturbation Hamiltonian, operators evolve according to the unperturbed Hamiltonian. So it's a mix of the Schrödinger-Heisenberg picture. And that is simple because then we always only have to deal with the perturbation Hamiltonian in the equation of motion for the reduced density matrix. This is for the entire density matrix. Formally, we'll proceed by integrating by steps, so step by step. So we do a first integration formally. Integrating this expression, we get some initial condition, which sometimes is called as the memory term, whatever is the system at time equals 0, and then a first term in a time evolution, having simply integrated it formally. And now we start iterating. So we plug this expression into here and integrate again. So we get the memory term, which now is the commutator between the interaction Hamiltonian and the density matrix at the initial time, and then a commutator of the initial commutator that we had here, having inserted into this commutator, we get a double commutator. Okay, and formally we can take the trace now out of the irrelevant degrees of freedom, which is the phonons, and get to first order, second order, which is say the leading order in a perturbation Hamiltonian, which is second order in alpha. If I extract an alpha from this term, I will get an alpha square here. An equation of motion for the reduced density matrix. Notice one issue that I didn't emphasize last time, and I should have. It's a problem that we'll see even later on in a different context. We end up with a system which is not closed, mathematically is not closed. If you count how many one-particle operators we have here, we have two coming from the fact that we're dealing with the density matrix, the off-diagonal and diagonal elements of the density matrix, the reduced electron density matrix. In this row, we have another pair, because this contains again a term of C dagger C, and here we have a C dagger C in each term. So this will be a 6 or an 8 particle operator. We'll see that we'll reduce it to a 6 particle operator later on. So the point is that we start from trying to derive an equation of motion for a two particle thermal expectation value or ensemble average over the phonon degrees of freedom of our electron states, but we end up with an equation which has additional terms. So this is a hierarchy that you find in every expression that you find trying and solve perturbatively equation of motion for quantum transport has a complicated acronym, BBGKY, from the name of people who independently approach the problem. It has different terms depending on the context in which the quantum equation of motion are dealt with the block operator of motion, the Heisenberg form for these operators, density matrix, Green functions. No matter how you formulate the problem, you end up with this nuisance of having a hierarchy of equations. So you start with a 2-particle, and then you need many more particles, or in principle you will need to find an equation of motion for a many particle state, and so on. So in some sense you have to close the system, and that's what we will do, essentially using the Hartree-Fock approximation for the many particles operators, having already used Van Hoff's argument to reduce the number of particles operators that we have here by a factor of 2. That's why we'll lead only a 4, and we'll end up with a 4-particle operator eventually, thanks to the Van Hoff argument. So far, everything is correct up to second order in interaction Hamiltonian. Now, we make the assumption I already said. We will assume that at t equals 0, the phonons are at thermal equilibrium, and they always stay at thermal equilibrium. So actually, there's no time dependence here, because we will assume what sometimes is called the Markov approximation. And we will assume that at every time, electrons and phonons are decoupled. Again, this is another assumption that in some cases is not true. I mentioned last time some studies that have been conducted of what happens to a system of electrons like gallium arsenide, in which a laser pulse generates a distribution of hot carriers in a conduction band, and then with another lower frequency laser pulse, the probe pulse, you look at the Raman spectrum, and this gives you an indication of the distribution of the electrons as they relax in time. And you can study the time dependence by varying the delay of the probe pulse from the pump pulse, which has excited the carriers. And a study of this system shows that at very short times, actually you have states which are not really pure electron eigenstates, not purely phonon eigenstates, but a hybrid or coupling between these modes. So we'll ignore this complication and assume that this is always true, and this will be extremely useful in simplifying our states. By the way, as a matter of notation, this, for example, implies the trace over the phonon degrees of freedom, the relevant degrees of freedom, or in this case, it's just the phonon density matrix, but we will take the trace over these states. And as a matter of notation, these curly brackets mean simply the set of all possible occupation states of the various harmonic oscillators or states in the Fock space that we have for the bosons, for phonons, and for the fermions, which are the electrons. So the curly bracket means whatever is the particular Fock state that we're considering in Fock space of electrons or phonons, and they're just decoupled, or the total Hilbert space is the tensor product of the two Fock spaces, thanks to this approximation. Okay, so what we do, let's go here, let's continue. This is the equation that we had. One can see immediately that the first term, the memory term, having assumed that the phonons are diagonal at any time, and particularly at the beginning, you see that here we have an electron phonon Hamiltonian, which is one phonon term. So if we take the trace over the phonon degrees of freedom explicitly over here, we're summing over the diagonal of, if you want, the expectation values of the matrix element of this term. These have a particular number of phonons, the same in initial and the final state, but the electron phonon Hamiltonian has one phonon operator. So no matter what you do, this is going to vanish. Both of these terms vanish because we have a dot product between, say, consider the term in which we have a B dagger here. We have one extra phonons in momentum Q, if we have a B dagger Q, in this state compared to the final state. And so this is the dot product of two eigenstates of the phonon Hamiltonian corresponding to two different eigenvalues. Therefore, their dot product is zero. They're orthogonal. So the memory term disappears, assuming that the phonons are in thermal equilibrium at the initial time and decouple for the electrons. So we're left with this term, and this term is actually contains four terms. We have two terms coming from the commutator here, and then we have to take the commutator again with the electron phonon Hamiltonian at this different time. So we ended up with four different terms that I have written down explicitly over here. Of course, the order in which the various H's and the rho happen is important. It matters. This is already a hint that out of these four terms, you are going to get one pair of terms will represent in-scattering and out-scattering terms for emission and absorption processes. So in principle, if we think about the collisional term of the Boltzmann transport equation as we formulated before, we are in the good path towards approaching that. Now we have to manipulate a little bit these messy terms, and again, this has two electron creation operator. This has two more. This has two, so we end up with an 8-particle Green's function, so to speak, or operator here, and we'll have to do something in order to close the system. This is just a reminder of what we mean by the phonons at equilibrium. Whenever we have a trace over phonon degrees of freedom of this object, only the diagonal term survives, and we have that this term is just the number operator of the thermal equilibrium function of the phonons and momentum q, which is equal to q prime. So phonons are assumed to be a thermal equilibrium, so it's just the Boltzmann, Einstein-Boltzmann Bose distribution function. Okay, so now we're left with this piece. I took out the alpha square. I have to express explicitly my electron phonon Hamiltonian. This is one of the terms that we have here, particularly for phonon absorption in this particular case. And I have inserted explicitly the time dependence of the operators. Remember that all operators that we have here depend on time according to the Heisenberg picture for the unperturbed Hamiltonian. So we can simply express it in terms of the eigenvalues of the various states I, J, L, M, and so on that we have here. And the net story will be how to perform this integral in a way that simplifies this expression and reduces to the Fermi-Goldman rule. Now, the crucial step is this is the same term, having still kept hidden the time dependence of these operators. Remember that this is also dependent on time, although not explicitly noticed, depends on time t in this case, via the time depends in the Heisenberg picture for the unperturbed Hamiltonian. The idea is that if we have a term like this, and our system now interacts with a bath, which has very many degrees of freedom, we can do a little bit of a trick. We insert a completeness, which is a sum over all electronic states. These are states of the Fock space for our fermions, and we insert a completeness. This is the identity operator, sum over this big m's and little m over these states. It's just the identical operator in the electron Fock space. So we can do that, since we're tracing over the phonon degrees of freedom. We're taking the statistical average over the electrons. Now, these states, there are very many that contribute to this sum. The matrix elements that we have on the right and on the left are non-zero for a huge numbers of these states, simply because you have lots of phonons. Our bath has very many degrees of freedom. There are lots of phonons that can give you non-zero matrix element for different states, big M sub n and big M sub n. So this is something that I didn't say last time, but it's extremely important. This is the fact that you have very many states that contribute to this sum is due to the fact that we have very many degrees of freedom of our thermal bath. Now, we have a sum over these states. The first term here will have different phases. So we have essentially the matrix element between C dagger I, Cj times this object and this object as a final state. And we have taken the sum over these If the initial state, so to speak, which is this object here, and this state are different, the phases of these two terms will be distributed at random. They will all be different. If instead this state and these states contribute with a fixed phase, then, so they are the same, so to speak, then the phase of these two objects will cancel exactly. So when we have I and j which are different, the sum over these terms will involve a sum over terms which have a random number of phases. If instead I and j are the same, then this state is essentially a multiplication is parallel to this one, so to speak, because this will be just the number operator, which is a number acting on this state. And then the phases of these two terms will cancel exactly. So the sum involves a number of n squared terms, where n is the number of terms that contribute to the sum, which is very large because it's roughly proportional to the number of phonos that can give non-zero matrix element here, and there are very many of them. On the contrary, if I and j are different, then the phases will essentially interfere at random, and we'll have roughly a term which, a number of terms which goes linearly with the number of phonos. So in the limit in which the number of phonos, or the number of degrees of freedom of the bath, is very large and goes to infinity, we can ignore the off-diagonal elements. This is the basic argument that Van Hove gave. Van Hove went beyond Pauli because Pauli assumed that at every time step you have to do this randomization by hand. Instead, Van Hove shows that you have it as long as you have a very large number of degrees of freedom in the bath, and as long, and this is something that I will be a little bit cavalier about and not go into details, and as long as the initial state that we're dealing with, remember we're starting with electrons which have been injected from the contact of equilibrium, and then we shut down the contact, or we have optically excited the system of equilibrium. No matter what, we have to make some assumption about what is the initial state that we have. Van Hove said that we can have this cancellation of phases, so we can ignore the off-diagonal elements of the density matrix expressed on the basis of our eigenstates of the unperturbed Hamiltonian, as long as the initial state essentially is very narrow in energy or is very broad, one of the two. So it's very well localized spatially or very well localized in momentum space. I remind you that Van Hove did not exclude the possibility that other initial states satisfy the criteria that he set forwards to prove the master form of the collisional operator, but he couldn't find any. That's what he says in a paper. So if we assume that our initial state, for example, is a very tight distribution in energy, which means essentially we're injecting plane waves in the system, which boils down to the fact that we're considering a region of our semiconductors which is much shorter than the size of the wave packet we're injecting. So much shorter than the coherence length, the average coherence length of the electrons. So we're dealing with short devices, we're a short region. That's what we will use later on when we will have to take a large device and slice it into small regions which are shorter than the coherence length of every electron. So having done that, we can use this Van Hove argument and say that we will consider only the terms in which I and j are the same. So only some terms survive, only the diagonal terms of the elements of the reduced electronic density matrix. Now we have to go and do a lot of considerations that I will be a little bit nonchalant about and skip most of them. This will happen also on a very narrow range of times, t and t prime, in this integration in which can happen. At the end, we're left to the fact that only terms of this form contribute. Again, we have the ci and j. The j went away to be replaced by an I because we're considering only the diagonal terms. Now we have a 6-particle operator. However, notice that this is the number operator. This we can bring it out. If m is different from I, we can anticommute this twice. And we have the square of the number operator here. But the square of the number operator is the number operator itself. Because for fermions, the number operator of state electron state I. Remember, I can include spin as well, right? So we cannot put more than 2 electrons in a single state, so this n is either 0 or 1. So the square of 0, 1 is the same. So we can reduce it out of, how many did we have? 8 particles operator at the beginning. We had only 4 particles operator. Not only that, but you see that you have only 2 indices here. So this is sort of a density correlation function. This is the number operator of electron in state I. This is 1 minus the number operator in state M because of the anti-commutation that I would have to do here. So this is a much simpler form. And we can actually now reduce it even further by assuming a Hartree-Fock approximation. It's Hartree, but indeed, since these guys obey canonical anti-commutation rules, we have the Fock part, the Pauli's principle, if you want, already included. So we replace these by their thermal ensemble average, if you wish. And now if we plug it back into these expressions, I should look at, where was it? I apologize. The one with all the, here it is. If we plug now back, all of this guy has been reduced to the I and J equals equal, L and M equal, also equals for the same reason. H and R equals also to L and M. We have reduced this to a two density operators, or a density correlation function, or a 4 particle operator, but with I and J equals and L and M equal. So there is a huge simplification in these coefficients. And if you do all your algebra carefully, then you're left with this expression. All of the other indices have disappeared. We are left only with an I and an M. This is just the time dependence of the phonon operator. And we have that this entire term has something which begins to look like a master's kind of operator. This is some scattering kernel, let's call it. I've reintroduced the fact that we have many phonons in principle, phonon branches. So I've introduced this. I'm considering only phonon absorption for now. So we have, remember, this is the term that expresses one of the contribution to the time derivative of the density matrix, the diagonal term C dagger ICI. So this is the occupation of the state I. This term represents how fast the occupation of state I evolves in time. And we see that the occupation of state I decreases because of the minus sign that we have here, decreases in time according to the probability that the state I makes a transition to a state M, a different state M. Summed over all possible final states M, transitions mediated by all possible phonons eta, and you see that there is also the Pauli blocking term. This transition can occur only if the state M is unoccupied, is empty, and so we can scatter into there. So this is sort of what we would expect. The occupation of a given state decreases because the state electrons can scatter out of this state. So this is an outscattering term for phonon absorption only, and still is not quite the form that we're familiar with, because this depends, and this is crucial, depends on the past history of the system. There is a time dependence of what the system looked like in previous times, from our initial time in which the interaction is turned on, for example. And this has a very similar expression to our Fermi golden rule. Okay, there's not 2 pi over h bar yet, it will appear, but there is a square matrix element of our interaction, and something which is not quite a delta function, but it's an oscillatory term that for very large t minus t prime gives it a delta function, right? And this will be what we will have to do next, taking the Van Hove limit, which is completing this collision. So this is what we have for a transition, let's say, perturbation theory, even in conventional quantum mechanics, at short times. The system has not collapsed to a particular final state conserving energy, but it's in a linear superposition of states which are off shell. By that I mean do not conserve energy. And the shorter the time, the biggest, of course, could be the violation of energy conservation by one of the popular form of Heisenberg principle, although that is not exactly the delta E, delta T roughly equals to h bar is not exactly Heisenberg principle, but simply because time is not an operator. Anyway, so we see that it looks like what we have in mind. This is the Einstein's coefficient for phonon absorption. We have a square matrix element. We have something which depends on energy, although it's not quite the delta function yet, and we sum over all possible processes Q. So promising, but not quite there yet. And indeed, if we put together all of the various states, remember this is again a rephrasing of what I just said. So if we put together now various phonons, emission processes, absorption processes, and so on, I still stick to only absorption in this particular case. But if we look at the other term, it's a complex conjugate of this term that we just discussed. By the other term, I mean these four terms that we have here. We looked at one, we're considering the second one. So what we have is something which, if we sum over plus or minus as well, it looks like a master equation that occupation of a particular state I, again, this is C dagger I Ci, we're not considering off-diagonal elements of the density matrix anymore, decreases because of outscattering terms, which is just what we saw before. This state I has an occupation that decreases in time in a way which is proportional to the occupation itself. Of course, the probability that an electron scatters out is all of the electrons scatter out is proportional to the number of electrons that we have. It can scatter to a state M as long as the state M is available. Similarly here, the occupational state I can increase because electrons in all of the other states M can scatter into the state I as long as the state I is available, is not occupied. The only difference between this and the collisional operator of the Boltzmann equation is this integration over time. So the tricky thing here, which is a little surprising, is we made lots of assumptions. We have assumed that the electrons or phonons are at equilibrium, at T equals 0, decoupled for the phonon, for the electrons at on time. So the density matrices for electrons or phonons are just decoupled, and the total density matrix is just the tensor product of the two. We have assumed that the phonons remain at equilibrium always, this Markov approximation on the phonons, and yet you realize that if I change T to minus T in this expression, I swap essentially these two terms and I get an equation which is reversible, time reversible. It's invariant under time reversal. Again, the fact that we kept the phonons at equilibrium, it does not, let me put it another way, we have not erased any information in our model because we never put any information about the dynamics of the phonons already at the beginning. We're already assuming they're at thermal equilibrium. This is what Zwanzig, a famous name in quantum statistical mechanics, called the pre-master equation. It's almost a master equation. This is almost the form of the collisional operator that we find in a Boltzmann equation, but not quite because there is this integration over time. Again, physically, this is very important. We are not making any assumption, the Stotz-Allen-Satz, the molecular chaos approximation. The collision terms here, the scattering kernels, do depend on the past history of the particle. So they are not instantaneous. They may not be local. I gave you the analogy of scattering with one impurity and then scattering with the next impurity nearby. Scattering with the second impurity is different from, say, the cross-section will be different from the cross-section for the first impurity, because the incident wave on the second impurity is now a linear superposition of the original incident wave and the wave which has been scattered by the first impurity. So the history of where the first impurity was is hidden or is represented by the time dependence of the scattering kernel. We have to keep track of what was the history of the system in a state M before the collision. So this is the crucial point. Now, in order to get the full master form of the collisional operator and so get the Boltzmann equation eventually, we have to get rid of this time integration. And this is what is done by Van Hove. Van Hove took the limit. Let's call this variable alpha squared t minus t prime. T minus t prime is everything depends on this in the scattering kernel. And let's rewrite just the out term in terms of this rescale variable in which now our time is hidden inside this parameter tau. And let's take the limit in which this goes to infinity. So the time t goes to infinity for a fixed t prime as the strength of the interaction goes to 0. This is necessary. Let me go back to the expression, this expression here. You remember that for the Fermi-Golden rule, in order to integrate this, we have a problem, right? We integrate over time, or t minus t prime. We get this term in the denominator, but then we sum over q, and clearly we're going to hit a problem. We're going to hit a singularity when h bar omega q is equal to the difference in energy of the two states, which is exactly the situation in which we would have energy conservation, which the two states are separated by an energy which is equal to the energy of the phonon which is emitted or absorbed, in this case absorbed. So in order to regularize this integral, we would have a pole, we have to use the Kramers-Kronig relationship, the famous Tsiolkovsky-Pamelji theorem that I don't know how to pronounce, in which we have to regularize this integral. So before taking the integral, we have to add a exponential of minus st minus t prime, or s minus st, and then take the limit of s go to 0, which means moving the pole a little bit above or below the real axis when we do a contour integration over q, for example. So this is the same trick that we have to do now. We do it to get the Fermi-Golden rule, and indeed we will get the Fermi-Golden rule. So in order to regularize this integral, we add a little bit of a regularizing term. I call it eta here. Bad choice of nomenclature because eta was the branch index of the phonons. Let's call it s instead. And then we'll take the limit of s go to 0. In this case, we recover exactly Fermi-Golden rule because that's the integration that we have to perform. Oops, where am I? Sorry. This is the integral that we have to do over time, having added that little real exponential, and then we get the delta function. And so we recover the full master equation in this form. There's no dependence on the past history of the particle because we have completed the collision. It doesn't depend anymore on the past history. I'm at a loss of words for saying what is the physics behind it. I'm very puzzled. I'll be glad to listen to any suggestion, but it looks like we have done the major conceptual step of moving from an equation that is invariant under time reversal to an equation which is fully dissipative, is not time reversal invariant anymore. If I change t to minus t, things don't change that simply. We go from a universe in which entropy decreases to a universe in which entropy increases in time if I change t to minus t. So clearly I get a different picture. But the whole trick on how to go from the pre-master equation to the master equation is simply because of having taken this Van Hove limit of a weak collision. I think it's kind of disappointing in my view. What is physical meaning of this parameter called here eta, called it s in words? 1 over eta, or 1 over s here, is essentially some decoherence time. I don't know if you heard much about alternative explanations of the interpretation of quantum mechanics. It may be related to the Gherardi-Weber-Rimini universal time constant, which is the time scale for the universal collapse of a wave function. It's whatever it gives you the coherence on a system which has very many degrees of freedom, which remains a mysterious object. So we can derive, and that's why I use the word derive in quotes, the master form of the collisional operator for the Boltzmann equation only by having made this disappointing mathematical trick, a regularization of an integral and then taking the Van Hoff limit. So this remains the main mystery, and I do not have a solution, of course. I wish I had. And this is the only way in which I know you can go from Liouville von Neumann to Boltzmann. At some point, you have to break this time reversal symmetry, and there is no formally rigorous way of doing it, as far as I know. Many proposals, many ideas. Of course, in classical mechanics, the problem can be formulated in some fashion. In quantum mechanics, we have the additional complication of the fact that the Copenhagen interpretation itself, with a collapse of the wave function, introduces some sort of irreversibility when you perform a measurement. Now, a phonon being absorbed or emitted by a system of electrons, by an electron gas, is a sort of a measurement, because we don't keep track of the phonon anymore. So in a sense, irreversibility is again due in quantum mechanical terms introduced by the electron-phonon interaction, simply because the thermal bath is so big, it performs a measurement, so to speak, even if we don't look at the results of the measurement, simply because of the large size of the system with which our electron gas interacts. Okay. So far, again, please stop me if you have any question. So we're almost there, but not quite. So what we've done is we've looked at our system. It was described by a diagonal density matrix at t equals 0, phonons at equilibrium, electrons were instead in some off-equilibrium distribution, but diagonal. Then we let the system evolve, and assuming that the size of our system is shorter than the coherence length of the wave packet we have injected, packets that we have injected into the system at t equals 0, or that we have excited optically, then we could formulate the decay towards equilibrium in a way which is much simpler than what we would have. We consider only the diagonal terms of the density reduced electron density matrix. I remind you that this rho sub I is C dagger I sub I ensemble average, thermal average if you wish. So in a way that is perfectly intuitive, and it's exactly what Pauli derived in the early 1931, whenever it was. No, actually 1928, right? I think I gave you the reference last time. So, however, we didn't have to make a random phase approximation on every time step. We had to assume that the system interacts with a large thermal bath with a lot of an infinite number of degrees of freedom, and we had to assume that the either the collisions are very weak or that the time goes to infinity, or a combination of both, according to the Van Hoff limit. The system is still closed. This equation does not have any term that expresses the exchange of particles between the system and contacts, reservoirs. So now we do extend our picture by assuming that instead we consider the same situation that we have considered before so far, but the system is in contact with reservoirs. Let's consider just a one-dimensional system, a contact on the right, a contact on the left, and we do a phenomenological idea. What do contacts do? The left contact, so we will add to our equation here another term, if you wish, which expresses the time derivative of the occupation of each state I according to the drive of the contact. And say the left contact, for example, will inject electrons if needed. So here we have a term which represents a flux of electrons which are coming in or getting out. A contact, the left contact, for example, our source. This term will be positive, so electrons will be injected into our system. If this is well, extracted or injected, depending on which sign I have, in a way which is proportional, linearly proportional to the deviations of the occupation from thermal equilibrium. So if I have a distribution function of the contact attempts to keep charge neutrality in a region adjacent to the contact. In our case, we're fully non-local, so an entire device. So it injects electrons if the distribution function is smaller than the equilibrium distribution function you want, or vice versa. This is actually represent the change in the contact. And this is just the Fermi-Dirac distribution function. So this is a phenomenological way. Separating the Hamiltonian of the contact from the Hamiltonian of the device is always a tricky business. And strictly speaking, it makes no sense. Nevertheless, it's convenient because whenever we study a system, we have to put boundaries on the system at some point. Whether we, numerically for sure, but even conceptually, it makes it much easier. So even in Landauer formulation, even though Landauer himself said that we cannot split the Hamiltonian into a device and the contact parts as simply as that, nevertheless, this is the formulation that we usually assume. So the contacts will inject now, depending on whether the left or the right contacts, whether we are away from thermal equilibrium or not. Of course, when rho is equal to the equilibrium distribution function in the right contact or in the left contact from the other expression, the contact doesn't do anything. And instead, the particles are absorbed if there are too many. This flux term will be simply proportional to the velocity in the contact. So at the end, we get an equation. Now I put a lot of indices. There is an extra index S that labels the contact, left and right. So we have a master equation. I apologize, at 10 o'clock over here. So it's the same form of the master operator, collisional operator that we saw before. I've added the little index S expressing the left and the right contact, or more contacts if you consider a more general geometry, like for example, a planar MOSFET or a double gate MOSFET, in which you also have a current flowing in and out of the gates. If you want to consider gate leakage, for example, we may have more contacts. In general, for example, the description that Lenter-Kirchner gave about the quantum transmitting boundary method, you can have more than one contact, and you can express the states and eigenstates of a system in more than one dimension. But this is the same master operator we saw before, and this is just the effect of the contacts, which is the occupation which is maintained, or the contact attempt to maintain equilibrium, charge neutrality, sorry. So how do you view the picture? This is assuming that this equation actually represents transport of electrons in a system which is short enough so that we can use this master form of the collisional operator, so that we can assume that plane waves are injected, or the scattering waves that we have, eigenstates of the unperturbed Hamiltonian. This is the unperturbed Hamiltonian. This is a potential, source, drain, emitter, collector, whatever you want to view. This is a potential of a device, the active region of the device. This is my boundary. These are where the contacts sit. They're represented by equilibrium Fermi-Dirac distribution, and they keep injecting. The red waves are scatter waves which travel from left to right. The blue waves travel from right to left, and the contacts just attempt to maintain thermal equilibrium of these states. So each of these states, and finally we see what they are. This is state I, this is state I prime, this is state J, J prime, and so on. So these are the various states that we're considering, and we want to consider transferring this device. Again, short enough so that I can use a master form for the collisional operator, or I can describe it with a master equation. What I do at thermal equilibrium, in a ballistic case, we have contacts which are trying to inject proportionally to the deviation of the states away from thermal equilibrium. There are some transmission and reflection coefficients here which you can ignore for now, just the normalizations. So simply the contact will maintain a thermal equilibrium distribution. The left contact will maintain a thermal distribution of the red states and the drain contact of the blue states. So clearly, if I have a Fermi level, which is here, these blue states will be empty in most cases. If I have dissipation, so if I have inelastic collision between the states, electrons that can scatter from one state to the next, I reshuffle the occupation of these various states according to this master collisional operator, which is our Boltzmann-like collisional operator. Okay, good. Finally, on to Boltzmann. What do we do now? So now I want to study a device which is instead much longer than the coherence length of the electrons which are injected from the contacts. So the master form of the collisional operator cannot be derived following the procedure that we followed so far. So if I have a device which say is a silicon device and the active region of the device is 5 nanometers long, good. Probably I can use this. Scattering is relatively weak. Transport is mostly ballistic. I can describe deviations from ballistic transport in a leading order way with the Pauli master equation. But if this device is 200 nanometers or half a micron long, or as it used to be at the dawn of the microelectronic era, if it is 10 micron long, clearly I cannot do that. The coherence length of an electron may be of the order of a few tens of nanometers at best. So clearly this violates the criteria set by Van Hove. Instead, let's do that. The Boltzmann equation is expressed in terms of position and velocity of wave vector. So in order to get closer to that form, let me make a change. Rather than consider the density matrix expressed over the eigenstates of the full Hamiltonian, including the external potential, they don't make much sense in a very long devices because of the strong decoherence. Let me consider instead plane waves. So I get exactly the same formulation that I had before. The Liouville von Neumann equation can be remanipulated, and with the whole set of assumptions that we made, I can write it in this way. It's a master equation, the occupation of a state K. I explicitly wrote two indices to say these are the diagonal elements of the reduced electron density matrix. And I'm ignoring the generacy effect, so I'm assuming that the occupation is very small, so that I can ignore Pauli blocking. So the occupation of a state K can increase because electrons in a state K prime can scatter into K. This is the scattering probability per unit time, or the scattering rate of going from K prime to K. It can decrease because electrons in a state K can scatter out to different states K prime. Then I have the effect of the contact. However, since I'm considering plane waves, I'm not considering eigenstates of the Hamiltonian that already includes the external potential. I have to put it by hand. So, of course, I have to add a commutator, which is the equation of motion of the density matrix, of the KK element of the density matrix with the external potential. Let me call it minus E because I'm assuming electrons. E is the magnitude of the electron charge, and phi is the external potential. Now, this commutator can be evaluated relatively simply if I assume that now I take my device, I slice my device into many slices, which are each of them shorter than the coherence length. So in each slice, I can use this expression, okay? Now, in each slice, I assume that the potential changes linearly. So I linearize it, so to speak. So in a slice, call it J, the potential can be written as the potential at the left-hand side of the slice, and then a term which represents the slope of the potential. So the field, the electric field at position J, at the left-hand side of the slice. Now, in this commutator here, we'll have the density matrix, which is the C dagger C, the only variable that I have here is the variable z, which is the position operator along the z coordinates. Okay, but now remember that if I take the multiplication by z in Fourier space, because I'm taking the Fourier transform by taking the matrix element among the plane waves k, multiplying by z is equivalent to taking the derivative with respect to kz, much as in Fourier space multiplying by momentum means taking the derivative with respect to the coordinate along the direction of the momentum. So what we have is that this term becomes simply proportional to the electric field and the gradient in k space of the density matrix. Now, the context, how do I represent the context? Remember, now I don't have context anymore, except that at the far left and the far right of my device. So the context is actually replaced by the occupation of the adjacent slices. So what, according to the phenomenological model that we had before, I replace the effect of the contacts from the right by a distribution function which is attempted to keep at the same value that it has in a j plus 1 slice, and the flux is given by the velocity of the electrons at that particular slice. So in the limit in which I make the slices very thin, of a thickness delta z, which is smaller than the coherence length of the device, what I have is that the derivative of the occupation of a state k is given by the usual master form of the collisional operator, the time, the gradient in k space of the occupation itself, which is what we get from the commutator here, and then the effect of the contact in a limit in which this is very small. This becomes the derivative spatial gradient, if you wish, along the z direction of the density matrix. This now becomes a function of k and position, by the way I've defined it, rather than expressing it as position j. I express it in terms of a continuum in the limit in which the thickness of the slice tends to 0. Notice that the injection from one slice to the other is incoherent, so there is no quantum coherence between one slice and the other. And then what I have is, you recognize that this is just the Boltzmann equation in one direction, because I've assumed a one-dimensional transport problem. So the derivative of the occupation, and now we can call the distribution function of electrons at position k in k space, and position z in real space, having replaced the index j with a continuum z, is given by a collisional term of the Boltzmann transport equation, which has the master form, and then we have the usual terms. The driving term, this is the drift term, and the diffusion term, which is proportional to the spatial gradient. We can generalize it to three dimensions, and we get the Boltzmann equation. Okay, in this form. So, we're taking a little break. Let me review the assumptions that we have made. These are assumptions that do not deal, so I'm not listed here necessarily the various approximations that were made to go from the Wien-von Neumann equation, so the quantum transport equation, to the master equation. These are different. We saw already that we made several assumptions about the decoupling between electrons and the thermal bath and the phonons, the fact that the phonons are always at thermal equilibrium, that the matrix element, the density matrix of the electron and phonon are decoupled at all time, and then the weak perturbation, and then we had to take the Van Hove limit. So these are a set of assumptions, approximations, whatever you prefer to call it. Some of them is, in my mind, it's not clear whether they are assumptions or approximations, or even axioms in some cases. Here it's a different set. Having obtained a master equation for transport over a short distance, what do we need to go from there to the Boltzmann transport equation? So we need to assume that electrons are described by plane waves, and yet they are given a position. So it's classical mechanics. So despite the fact that we're dealing with slices which are very thin, we still describe electrons by plane waves. And this violates Heisenberg principle clearly. So the idea is that the length scale, so electrons are described as wave packet, strictly speaking. These packets, however, are localized spatially over a distance which is much shorter than the active size or the size of the active region of the device. And in terms of momentum space, their broadening in momentum or in energy, it's much shorter than the typical energies that we have in mind. So they're broad enough to have a weak or a small uncertainty in momentum and so in energy, less than kT, and yet they are narrow enough so that their uncertain momentum is smaller than the length scale that we're dealing with. So this constrains us to very large devices. So it's an issue, okay? Although there are reasons why one can assume that semi-classical transport can be a very good approximation, even a short length scale, but in principle, we do not expect that. We have assumed that the electric field is weak so that we can actually use perturbation theory here to linearize the potential. And all other perturbations are weak. This is already implicit in the master form of the collisional operator. Excuse me. There are other considerations. One advantage of what happened in the past when, in order to do a bibliographic search, you had to go physically to the library and physically handle volumes, is the fact that I once discovered a paper that I was not aware of. I was looking at the paper by Bardeen and Shockley about the deformation potential theorem. Next to it, I forget whether just before or just after, there was a 2 or 3 page short paper by Bardeen and Shockley themselves, and they were discussing the limit of the highest electric field in which the Boltzmann transport equation is valid, both from the perspective I just described, and also from the fact that there are several corrections that in principle one can add to the Fermi-Golden rule when you have a very high field and very high scattering rates, what's called collisional broadening, intracollisional field effects. We saw that the duration of the collision actually that we're assuming is infinity. We can talk a little bit about what that means. It's much larger than some time scale, and I think the time scale is essentially the fluctuations of the energy of the system, so a little bit tricky. But we're assuming that the collision lasts a very long time. If the electric field is very large, the energy that the electron has at the beginning of the collision can be different from the energy that the electron has at the end of the collision, whatever is the definition of the duration of the collision that you want to talk about. I'm open to discussion here. They're very tricky businesses. But nevertheless, these intracollisional field effects have been studied, and they sort of contribute to a broadening of the scattering rate. So Bardeen and Shockley dealt with the validity of the Boltzmann approximation, the Boltzmann equation. For example, you need a small field in order to avoid interband tunneling, as we saw also for the effective Hamiltonian that we discussed in the past. And we also have to worry about the fact that at very high energies, very high fields, which induce those high energies, Fermi-Golden rule may be violated. You get scattering rate which increase tremendously with energy, such as impact ionization, and then you have to worry about the broadening of the electronic states when the scattering rate is so short. In short, for silicon, if I remember correctly, Bardeen and Shockley in this little paper that I didn't know about, that happened many years ago, when I used to go to a library physically, is about the order of a megavolt per centimeter, so relatively high field. So we don't have to worry too much about it, but again, it's an issue that we have to consider. And all perturbations must be weak, and this is generally true in order to express collisions in terms of Fermi's Golden rule. There are cases in which this may be tricky. And indeed, I've seen, and it's not uncommon to see scattering rates in 10 to the 15 per second. And this is beginning to be a little, how could I say, it makes me uneasy to think of scattering rates which are so large. Yet, the problem is if you cannot use perturbation theory, what else do you do? I think I mentioned, talking about superconductivity, the fact that there are not that many instances in history of solid-state physics, I think in general physics, in which you can get results beyond perturbation theory. When you do that, typically, it's an important thing, like superconductivity, like fractional quantum Hall effect, like quantum chromodynamics. These are results which have been obtained beyond perturbation theory, but they're very few. We also assume that coming from the Van Hove limit, we lost time reversal symmetry and so on, all processes are instantaneous, independent from one another. There's no dependence on the back history. And again, the perturbation is weak, and they're local in space. This is another major limitation. So coherent scattering with many impurities, as I mentioned several times before, is not accounted for, because I would have to keep what we call the pre-master form of the collisional operator in order to keep memory, to keep track of the past history of the particle. So we lost reversibility in time, and that's because we took the Van Hove limit, or essentially we completed the collisions. So these are major approximations. There is another one which we will make all the time, and I will not talk about it much more. We all assume that the electric field that I have here is obtained by solving self-consistently with my transport equation electrostatic problems, so Poisson equation, and not Maxwell equation, except in a case in which I'm dealing with laser simulation, for example. But in general, we're not dealing with electromagnetic propagation, and that's because the time scale in which everything changes in the device is still slow enough to justify what is called the no retardation limit, in which we consider the propagation of signals instantaneous in electromagnetic fashion. So we don't solve the Maxwell equation. This is something which is unrelated. I thought I would add it to the list of assumptions that we're making. So in addition to the approximations, assumptions that we already had to make in order to go from von Neumann-Liouville to the master form of the collisional operator, we have to make all of these assumptions in order to get back to our Boltzmann equation. So I think it's a good moment to take a break, give my throat a little bit of a rest, because now we're going to move, if I don't have any question, we're going to consider very briefly two generalizations. We have derived the master, this last line, which is the crucial one, the master form of the collisional operator in the case of scattering with phonons. So these W's represent, as far as we've done so far, only scattering with phonons. And we had to use the idea that we really deal with phonons because we assume that the Van Hove argument holds, since we have many phonons, so many degrees of freedom in the thermal bath. What about impurity scattering? Is it the same? Can I write, you recognize that if I go back to my representation in eigenstates of the full Hamiltonian, including the external potential, these terms disappear, and I'm left with this term equal to this one, plus the contact, which is the master equation. So is it true that I can derive a master form of the collision operator also dealing with impurities and electron-electron interactions? So I will discuss them briefly. I've posted already many slides. You see it on the lecture notes. It's for the impurity scattering, it's a similar but with a major difference, that it is not the number of degrees of freedom of the external perturbing term that matters, is instead the configuration average, as we discussed before, dealing with the usual firstborn approximation expression for scattering with impurities, whether it's Cornwell-Weisskopf for Brooks herring, as we discussed. But we will have to do a configuration average over the positional impurities. For the electron-electron interaction is more complicated. Electron-electron interaction is a four-particle operator, and that implies that we're going to get a huge number of indices that we have to worry about. So I will spare you the pain of going through the details, and the bottom line will be that as long as I'm dealing with a system with many electrons, so again the Van Hove argument, as long as I'm interacting with a large number of degrees of freedom and I can use a random phase approximation to get rid of the off-diagonal elements, then also the electron-electron interaction will be the Van Hove term, and I can write a collision integral of this form. If I have a small number of electrons, then I cannot. And I cannot say what small and large means. I think that means few electrons, but it's not easy to assess when the limit is reached. Of the electron-electron interaction, I will only want to show, and also for the electron phonon, what happens at equilibrium, that the master form of the collisional operator gives you reasonable results in the case of a system at equilibrium in which there is no external potential, so this term vanishes, and we will recover the Fermi-Dirac distribution in these cases for those two types of interactions, so electron phonon, electron-electron. So we'll go to electron impurity scattering next. Time for my espresso, and let's take a 5-6 minutes break. All right, are we back? Can we resume? Yes. No?
Yes, we are here, Massimo.
You're here. You're there.
Can I ask you a question? Because I didn't get a fundamental point. Okay. Can I ask you to repeat one of the points
Sure.
you illustrated before, the one about the Vanov approximation, when you introduce the identity matrix for the completeness, okay? Several slides before, where you justify the Vanov with the many states and the
here, this guy.
yeah, I didn't get the point. I confess I didn't get the point at all.
I didn't get it either. It's extremely messy. So the argument that Vanov gives is, so look at this piece. We have one state here, which is fixed number of electrons, a fixed Fock state, okay?
Okay.
Good. This is the same Fock state, but then I apply a C dagger I Cj, okay?
Yeah.
So this becomes a different state.
That's true.
Good.
Mm-hmm.
Now we have this thing in the middle. When I look at a state in which this is I and j are different,
Yeah.
this state is different. If I and j are the same instead, this state is just the number operator I acting on this one. If I have 0 electrons in a state I, this is 0, as it is 0 for this particular state I over here, or it's 1. So it's parallel, so to speak. Mm-hmm. This guy becomes parallel to this one. Okay. So the phase of these states and the phase of these states are the same if I and j are the same. They are different if I and j are different. And now I'm summing over all this term over here. If t and t prime are relatively far away, then what happens is that the phase of states in which I and j are different will change for every I or j, for every m that I use here, every state that I'm summing over, every Fock state that I have here, I will get a different phase. Instead, if this is parallel to this one, I get essentially the cancellation of the phases. This guy will be e to the I alpha, and this guy will be e to the minus I alpha. So the phases cancel. I should say, you get 1. So all of the terms in the sum over this big M sum m that I'm performing, all of these terms will give me a constructive interference, exact phase cancellation, where I and j are the same. Instead, they will give me whatever phases I have, a random number of phases when I and j are different. Therefore, the sum essentially can be limited to the case in which I and j are the same. If you wish, physically it means that I'm interacting with so many phonons outside. Remember, the number of phonons enters here because if I had only one phonon, there would be only one element, M sum m, which gives you a non-zero matrix element. But I have so many phonons that in practice, all of the electron Fock states contribute to the sum. So I have very many, thanks to the fact that I have many phonons. And each phonons contribute to a random phase when I'm going from I'm considering an off-diagonal term of the density matrix. I don't know if that is clearer. Mathematically, you can see it, I guess. Physically, what this means, it's related to the large number of degrees of freedom of the system and the fact that essentially you kill the coherence between the states I and j, because you can get there from so many ways that all the ways you can go from I to j have a different phase. And when you sum over all the possible paths that you follow from I to j, you get a random phase cancellation. I don't know if it clarifies if I look at the Feynman path quantization, going from I to j involves many paths. Each path since I have so many phonons that contribute, gives me a different phase. And by the time I get to J, I get a total cancellation of the phases at random. Instead, if I go from one state to the same state, I get exact cancellation of the phase of each path. So each path contributes with a phase of 1. And then they all add up. Any clearer?
Yeah, yes, it's better. I mean, you know, the point is that if the states are different, if the I and J are different, if you start from a different phase, actually, if it's different states.
If the states are different, you can get there through so many ways that all the phases with different phases that they cancel. Instead, if I and J are the same, then you always get there with the same phase. So you have constructive interference by the time you get there.
Okay, okay.
So I would tell you, why don't you read Van Hoff's paper? But
yeah,
that is.
I would like to avoid that.
I understand, I sympathize, and actually I agree. Particularly, as I told you, I quasi understood the first half of the paper. I got lost at the end when he really deals with irreversibility. By the way, it looks like the Flemish guys have contributed a lot. There is a paper by Van Kampen, who was written around the same time. It's a different story, but it's related to the collapse and how you can expect the collapse of the wave function to happen naturally from the fact that you have interactions with a system with many degrees of freedom. Similar things, but there the emphasis was not so much on approach to equilibrium, thermal equilibrium, but it was more on the interpretation of quantum mechanics. So one of the many attempts to give a formal proof to the Copenhagen interpretation. They're all doomed to failure, but there have been many attempts. And another paper that I didn't go through it here, it follows a very similar line of reasoning. You know, there are many attempts to justify the Copenhagen interpretation, starting from Van Neumann. Again, that was flawed in a tricky way, very similar to the claim that Boltzmann had of having proven the H theorem. So this is the best I can tell you. Mathematically, I think one can easily see it, that if this guy is parallel to this guy, so has the same phase, which happens when I and J are the same, then the sum that you have gives you constructive interference. And instead, if I is different from J, you get all sorts of phases. Physically, it's a little trickier to understand exactly what happens, but I think the best understanding that I have is through the Feynman path quantization, because you can see how the phases interfere destructively at random when I and J are different. And you have many phonons. The same thing will happen with electrons, and we'll have to go through there the same way. And here the sum would be essentially the same. I'll do it in a moment without going into too many details, but if you have many intermediate electron states, that happens when this involves many electrons, so put EE here rather than EP, it will be the same thing. If I have many electrons, then the same reasoning can be followed, and it's valid, because then lots of states contribute, lots of these virtual intermediate states contribute with non-zero matrix element. If I have only few electrons, then I have a few phases, and then this random phase cancellation cannot be used anymore. So in a quantum dot with 10 electrons, I don't know, with 10 perhaps is already a large number, but with few electrons, with 3-4 electrons, then you cannot use a master form of the collisional operator to describe the approach to equilibrium. I hope it's clearer. It's the best I can do. I hope so. It's the best I can do.
Okay,
it's a tricky
thank
business.
You in any case.
Okay. Impurities. And thank goodness they stopped mowing the lawn in front. The engine noise that you heard before was they were mowing the lawn just outside my window. Okay, scattering with impurities. So same thing, except that now our HEP will be replaced by HEI, I for impurity. And I remind you that the Hamiltonian for the scattering of an electron with an impurity is written this way. An electron with state I goes to state J because there is a matrix element or a vertex, whatever you want to call it, of this impurity scattering. Again, this is, if I and J are just K and K prime, this will be just the Fourier transform of the impurity potential at K minus K prime. And we have to sum over all the possible impurities. I remind you that even when we dealt with electron scattering with ionized impurities, we said, well, the process is not dissipative in terms of phase dissipation. I can very well take my numerical code that solves the propagation of waves in a given potential. I can put the potential of all of the impurities. There are some issues related to the singularities, but screen, for example, whatever. And then I get a current, a transmission probability, and this is a perfectly time reversible system, and I've solved my time independent Schrödinger equation exactly. If you want, it is also a problem that I can deal with scattering theory in quantum mechanics using the first Born approximation. So I cannot expect a phase cancellation of the Vanov argument be valid so that I can derive a master form of the collisional operator for impurity scattering unless I do something. I remind you also that the Boltzmann transport equation was derived by Lattinger and Kohn in, I think it was 1957, that famous paper for impurity scattering only, but they had to do something. They had to take an average over the configuration of the impurities, so where these R sub alpha are, these are the position of the impurities, and assume again a random phase cancellation coming now not from the many degrees of freedom that I have, but from the fact that I add up all of these phases at random, because I don't know what this R sub alpha is, or if you wish, the system is so large, my chunk of silicon, that every sub little chunk, gives a particular phase to my wave function, which is transmitter or scatter by that chunk. And if I get to the next chunk, all the phases coming from all of the other chunks will average out to zero, which is the same reason why we said I can use the first Born approximation and ignore scattering from other impurities as a coherent process. So we can follow essentially the same argument. This is exactly the same form that we had before, the Liouville-van Neumann equation for the from the reduced density matrix for the electrons. Again, a stop at second order in electron impurity Hamiltonian, not because it's weak, but because I can use the first Born approximation. So it's a different story. The actual electron impurity scattering is not weak by any means. The singularity can be 10 eV deep. So this is not a weak interaction. But I assume dilute impurities. Dilute means that scattering of the phase of the wave function which has been scattered by the previous impurity has been destroyed because of scattering with other processes. So dilute in that sense. Anyway, we can proceed as usual. We can do exactly the same thing. We have terms which involve now a little bit simpler, simply a density-density correlation. This means that the density of electrons I is correlated to the density of electron L in a state L via this interaction, the impurity interaction. And what I can do is exactly the same thing that we just discussed, except that now, rather than saying, well, I sum over many electrons, I say, well, these actually contribute to a different, if I take an ensemble average, unless alpha and beta are the same, they don't contribute at all. There is a phase cancellation. It's a pure random phase approximation, in this case, which is valid for diluted impurities. So same thing, let's say that the electron impurity interaction is of the Van Hove type. As long as it is weak, I can use the firstborn approximation, so I can ignore the coherence between impurity 1 and impurity 2, scattering for those impurities. So similar argument, but now the randomization of the phases is not due to the large number of degrees of freedom of the external system, because there's no such a thing. Impurities do not have internal degrees of freedom, but I'm averaging over the configuration average, the configuration in impurities. Okay, so this is just the same mumbo jumbo that I described. We can get to the same form of the master collisional operator, in which essentially what we do is we replace the square of the total potential with the so the sum of the potential squared with the sum of the square potential, so that it will become all the cross terms that we might have from this sum are cancelled out because of the random configuration of the impurities, which will give me a random cancellation of these phases if I go from one to the next. Okay, and so we recover the usual firstborn approximation. If you want to call it Fermi-Golden rule, call it Fermi-Golden rule, but it's really the firstborn approximation. Electron-electron interaction. This is a nightmare in terms of index algebra, all the indices that we have to deal with. You understand that it gets very messy, and that's why I don't want to go into too many details. If you're interested, ask me. Look at the slides that have been already posted on various places, on Teams and on the site of the class on the virtual resources. I think you can find all the files there. If you want to deal with the details about the indices, essentially what we have to do is assume that we have many electrons so that we can do this random phase cancellation and use the Hartree or Hartree-Fock approximation repeatedly to simplify the many particle green functions or expectation values that we have, ensemble expectation values that we have. You realize that when we do the same integration, stopping at second order in electron-electron interaction, now we have 2 particle operators here, 4 here and 4 here. So we have even at this level, we have a 10 particle Green's function. So we're starting to looking for an equation for the 2 particle, and we get a 10 particle. So there is a lot of work to do in order to reduce it to a set of 2 particle Green's function and close the system, the KK, whatever it is, GY hierarchy. So what we do is we do exactly the same. We consider the reduced density matrix for the electrons by taking the trace over phonons, already taken trace over the electrons. Now, this used to be the trace over the phonons. Now we have to trace over electrons because the irrelevant degrees of freedom are those of the other electrons. It's similar to the Hartree approximation, in which we say, I am 1 electron, I see all of the other electrons. Okay, let's average out the field or the charge, which is due to all of the other electrons, without worrying too much about the possible phases in which these electrons, the other electrons, may cohere. And let's assume that there are so many that their coherences are washed out by the randomness of the various phases in which they occur. So it's the same argument. I don't know, I don't want to go into too many details. You see that we end up with all these messy objects, and we introduce the same things, and we have to deal eventually with these many electrons approximation. I will not go into too many details. We use the Hartree-Fock approximation. The interesting thing, if you go into details, that we can clearly separate here between the Hartree, the exchange expression, and the fluctuations of the Hartree approximation. So it's a good exercise to go through the details and see where the various terms that we've been using, the mean field approximation, the exchange term, the fluctuations that described short range and long range electron-electron interactions as fluctuations of the Hartree-Fock potential will arise. But I will not, it's too painful. I mean, look at this. This is just something that you feel shivers down your spine when you see a term like this, and you have to say, well, I have to sort it out. Sorting it out always involves the same arguments that Van Hove gave. Is the same type. And the bottom line is this interaction has the same form that we had before. Some, as I said in discussing my attempted clarification before, there is a large number of intermediate states that give non-zero matrix elements simply because I'm assuming that there are many electrons in the system. And then I can use the Van Hove argument. Okay. What I want to deal with here, let's keep all of this mess. Eventually we'll find out a pre-master equation, which is of this form, in which I have, now it's a two-particle interactions. So we have that the occupation of state I has to be sum over all possible electron pairs, initial and final, partner electrons and L, and the final states for the pair of particles. And we have a scattering rate, which involves, of course, a pair of electrons in state I and L scattering to states L prime and N prime, and these are the usual density factors. So it's proportional to the number of electrons that I have in initial state I and L, and then, of course, I can scatter to a state L prime, N prime, as long as these states are available. They're not occupied. Again, I'll spare you the pain, but you recover the usual firstborn approximation for the electron-electron matrix element interaction. It's expressed in terms of these two-particle matrix elements, as we saw before, dealing with the electron-electron interaction. Again, you have to look for the exchange term and the direct term that we discussed before. The same thing, having taken the Van Hove limit. Again, I don't want to go into details because it's essentially the same procedure that we followed for electron-phonon interaction, except that it's way more complicated because of all the indices that you have, because it's a two-particle process. Actually, this is really the type of interaction that Boltzmann treated at first, originally. He didn't deal with phonons. They didn't exist at the time. Yeah, acoustic waves in crystals, maybe, but clearly not quantized forms of those. There was no quantum mechanics at the time. He was dealing with a gas in which two particles, I and L, can interact with other two particles, or so they can interact and go to two final states, which is essentially the term that Boltzmann used that gives the Boltzmann equation a nonlinearity. And indeed, if we go at the end, you see that the master form of the collisional operator that we get, and this is what we will get for the Boltzmann equation, is nonlinear. It's even more nonlinear than what it shows here. Clearly here it depends on the densities up to the third power of the density, if you're assuming a degenerate gas. Boltzmann did not know what degeneracy was, so these terms go away, but still this is quadratic. In addition, this expression itself contains the screened Coulomb interaction. Screening depends on electron density, so there is a sum over the density of all of the electrons involved in here. So it's extremely nonlinear, and this makes its solution quite complicated, and that's what we will discuss in the future. Okay, the one thing that I want to show though, so again, this is for the electron-electron interaction. Let's forget all the details about the mess that we have here. The logic is extremely tough to follow. Which term cancel and which do not, which terms survive, even having taken the Van Hove argument, having invoked the Hartree-Fock approximation and Markov approximation. It's still very complicated. But one thing that I want to show is this form of the master operator, as well as those, the same form that we derived for the electron-phonon collisions, are reasonable. So it's a sanity check, if you want. What happens at equilibrium? So this is my full master equation for an electron gas over a short distance. So if I want to describe quantum transport in a short device, in which I have the role of the contacts, the role of the electron-phonon interactions, this is what we derive for the electron-phonon interaction, and then this royal mess, which is the electron-electron interaction, this assuming that I have a degenerate situation, okay? And this F is the equilibrium distribution function. What happens at equilibrium? Do I recover out of this expression anything that makes sense? So I want to use detail balance, which is essentially showing that at equilibrium, whatever comes into a state has to go out, and they have to be equal, so that d rho dt is equal to 0. At equilibrium, I'm assuming that this is 0, but I want to show it. And I will use a circular argument in showing that ignoring this term, if I look at this will give me a solution which will be exactly f of I. There will be a big difference. So the idea would be that the Fermi-Dirac distribution is a solution of the equilibrium problem, so that this term goes to 0, and these terms cancel. This cancel this term, and this cancel this term, as long as rho has the form of a Fermi-Dirac distribution. The major difference is that if I consider electron-phonon interaction, the Fermi-Dirac distribution will be at a fixed temperature, which is fixed by the temperature of the bath. If I consider only the electron-electron interaction, so ignore interaction with phonons, just academically, just to see what I get, we will find that the solution of this problem is a Fermi-Dirac distribution function. So this equal to 0, this term is equal to 0 by itself. It's a Fermi-Dirac distribution, but clearly I cannot specify a temperature, at any temperature. So any Fermi-Dirac distribution at any temperature satisfies the requirement that this term goes to 0. Clearly, there's nothing that sets the temperature. In principle, if I start from an initial condition in which I have a given total energy of the system will evolve towards equilibrium, according to d rho I dt equals just this last term on the right-hand side, at a temperature which is consistent with the initial energy that I had. So a Fermi-Dirac distribution at the temperature such that the total energy of the system is whatever I had at the beginning. So the temperature will be set by the total energy of the system at t equals 0. But in general, if I consider just equilibrium without specifying the total energy of the system, I can get any temperature I want. The argument is very similar to the original argument that Einstein derived in order to obtain the Einstein coefficient. If I want by detail balance, this term must be equal to this one. So whatever goes from state I to state J must be equal to whatever, so from state J to state I must be equal to what comes out. Just for the sake of argument, we can assume that the energy of state I is less than the energy of state J. We have phonon emissions. We know that the emission that I need to go from state J to state I, since I'm making this assumption, will be proportional to 1 plus the number of phonons that I have. Let's consider just optical phonons, dispersionless, so with a fixed occupation number. So the ratio of this term over this term has to be equal to the ratio of this term over this term, and it has to be equal to this ratio, n divided by 1 plus n, which is exactly this Boltzmann factor. And so you see that plugging it into this expression over here, we have this relationship giving us the occupation of the state I and J, and we find that the solution is given by some Fermi-Dirac form distribution function, except for a normalization constant k over here, which is this constant. This has to be normalized such that the total number of electrons has to be fixed to the total number of electrons that we have in a grand canonical ensemble, and this must be fixed by the Fermi energy. So we recover exactly the Fermi-Dirac distribution at the temperature set by the bath. So good. So the master form of the collisional operator satisfies this sanity check in which at equilibrium we recover what we should have at equilibrium. For the electron-electron interaction is a little messy, as usual. So we have this detail balance requires that what comes in, what comes out is the same thing. Now this transition is given by the total probability that an electron makes a transition from state L to state I, which has to be summed over all possible collisions with all possible partners J, electrons in state J, ending up in state M. So it's a little messier, more complicated than what we had before. So we cannot derive the equilibrium distribution function from the property of the kernels because there's no external bath that sets any temperature, and we have not fixed the total energy of the system. So all we can derive is a general form for this distribution function, so to speak, rho, and see what form they have to have. We see that we can rewrite the right-hand side in this particular form, and we find that indeed a solution, if I don't write it here, but a solution has to be equal to the Fermi-Dirac distribution at some temperature. And again, the temperature is not fixed. So the general equilibrium form induced by the electron-electron interaction is the thermal distribution function at some temperature. This is a general property. Short-range electron-electron transition will attempt to thermalize the distribution function. So if I have electrons injected at high energy from the source, they will acquire energy from the external field. They will exchange energy and lose energy to the electron-phonon interaction, but the electron-electron interaction will not change the total energy of the system. Of course, energy can be lost only to phonons in this particular model, but the distribution function will be driven towards a Fermi-Dirac distribution. So it will be in a semi-log plot of number of electrons versus energy. It will try and make it at high energy like a straight line with the slope given by the inverse temperature, which is a general argument. I think we discussed it before. I gave you the example of sub-band gap impartialization in SOI, for example. The electron-electron interaction near the drain can induce high energy tails because it moves electrons from low energy and puts them at high energy by depressing the entire low energy distribution, so that total energy is conserved. Okay, this is all I want to say about the fact that we can derive the Boltzmann equation, or I should say, the master form of the collisional operator of the Boltzmann equation, also for electron impurity scattering, for electron-electron interaction, and electron-phonon interaction, and the electron-electron interaction at equilibrium give us the Fermi-Dirac distribution. At the bath temperature in the first case, at some temperature in the second case, but it's a Fermi-Dirac distribution. Okay, this was a long journey. As Professor Gnudi's question before reminded us, it's not easy to understand what goes on. And indeed, deriving the Boltzmann equation, I remind you again, is impossible. We need some trick in order to introduce to break time reversal symmetry starting from the Liouville-von Neumann equation, which is essentially Schrödinger equation. So lots of complications. Is the famous problem of what fixes the arrow of time in thermodynamics, in statistical mechanics, and that's an open problem. But I think at least now you have seen where the issue comes in, how mathematically one can deal with it, but the physical justification of taking the Van Hove limit, for example, it's kind of tricky. You can argue against it if you wish. Okay, so let's move on now to the final part of this Boltzmann equation discussion before going into some specific examples, and that is, how do we solve it? So this is our glorious Boltzmann equation. This is our collisional integral in the master equation form. By now we know that this is coming from Van Hove's argument and all the other approximations that were made. The Stoss-Hallan-Satz or molecular chaos approximation actually comes in from the random phase approximation and the Van Hove limit, especially the last one, completing the collisions. So using either Fermi-Golden rule or the first Born approximation to describe these terms. And these terms will be more complicated of this sort if we're dealing with the electron-electron interaction. So it can be more complicated than that in the case that I was showing on using a basis of plane waves, which is what we use to describe transport using the BTE. All these indices, I, J, L, M, becomes various K vectors. so plane wave states. So I didn't write it down here, and I've also assumed a non-degenerate limit, so the 1 minus fk, 1 minus fk prime over here. Those terms are assumed to be equals to 1 because f is very small. Okay, so how do we solve it? This is a partial differential equation, of course, in 7 dimensions, 3, 3, and 1. So 3 spatial dimensions, 3 velocity dimensions, or 3 Brillouin zone dimensions, and time. Nonlinear in principle because this term can be can contain f or some integral of f. So, and it's an integral equation. Here I'm summing over all k's. So it's a partial integral differential equation, nonlinear. So it is, I think, as nasty as it can get in terms of solving it. I don't know if I am aware of all of the possible methods of solutions that have been devised, particularly because the Boltzmann equation has been used in different contexts. For electrons, it's the case that we're dealing electrons in semiconductors is our interest, but we can have studying gases. I think that one of the big problems that, for example, was funded by the European community was the problem of studying the reentry of the space shuttle that the ESA was proposing. I don't remember how many years ago, before they canceled the project. The reentry in the early phases of the reentry in the upper atmosphere, for example, they cannot be studied with the continuum models because the atmosphere is so dilute that you have only a few molecules around, and yet they can create damage on the high energy, high velocity impact with the shields of the shuttle. Okay, the project was canceled, so nothing came out of it, but it was one of those situations in which we cannot use continuum method, you cannot use particle methods because you have too many particles. So there are different applications. A neutron transport in nuclear physics was the original way, the original context in which, for example, the Monte Carlo method was employed. Anyway, there are methods which are based on continuum, methods which are based on particles, methods which are direct. We will discuss in terms of the method of moments, various moments. I will consider the first, well, depending on how you treat it. If the 0th moment counts as 1, then drift diffusion is the 2nd moment. Energy transport hydrodynamic is the 3rd moment, although it involves the square, the 2nd moment, strictly speaking. Here, I think I'm embarrassed by the audience that I have because probably many of the people in the audience are better qualified than I am to talk about particularly the hydrodynamic model. Anyway, I will do the best I can, and please shoot me as soon as I say something which is incorrect, imprecise, or plainly wrong. Method of expansions, I think also some members of the audience have worked on expansions of the unknown, the distribution function, into various types of orthogonal functions. The most popular one has been spherical harmonics, but I think there have been expansions into Hermite polynomials, if I'm not mistaken. One can think of expanding into any basis set. Of course, one has to choose the best one so that since you have to truncate it at some point, you truncate it at the right point, or the few terms that you take capture the basic physics. Direct solutions, even today, even with today's machines and large amount of memory that we have, if you consider a 3-dimensional device time-dependent and you want to discretize the Brillouin zone in a sufficiently accurate way, the number of objects that you have to deal with, or the rank of the linear system, or even worse, the nonlinear system that you obtain by discretizing f is a little too large. For example, if you have a 3-dimensional problem, a 3-dimensional device like a FinFET, you want to discretize space, take 100 points minimum per directions in real space. That would be 1 million of points in real space. You have to discretize the Brillouin zone. You may take 10 maybe, but that's a little too few. I would say 100. So you get another 1 million points in a Brillouin zone. And so you get 10 to the 12 objects, and then you have to look at the time dependence. So memory-wise and computational-wise, a direct method is already out of the question, which is where the Monte Carlo method comes in, or which is a stochastical way of dealing with multidimensional system, or where continuum models come in, the moments method. So you don't have to discretize in k-space that way by making some approximations. Nevertheless, in some particular cases, they've been used. I should have talked first about iterative methods, but you can solve the Boltzmann equation by iterations, and we'll discuss this briefly. There are some historical interesting concepts here. The scattering matrix approach, this is something that I wanted to talk about. It was proposed originally by Mark Langstrom at Purdue, and since it turned out to be too complicated to be extended to more than one dimension, already in 2 dimensions they had problems. I could say its core idea became the source of the famous virtual source model that Mark Langstrom proposed. Don't get me started on this thing, but it essentially evolved into a intuitive, simplified way to deal with transport that has some merits, has also some drawbacks. I think the idea of using cellular automata, which is sort of a discretized version of either a direct solution or a Monte Carlo, somewhere in between. This is actually a pet project that Peter Vogel had in Munich. And they did a lot of work with Cometer and Serenity, and essentially it became a hybrid Monte Carlo method, but it's something that is interesting to look at. Jean-Pierre Degon in Toulouse had some model, some way to deal in a way which is somewhere between a direct method and a particle method, which is something that actually you can evolve the Monte Carlo method into. Rather than sampling particles which move under the field and the action of the field and the interactions, you consider a uniform distribution of sampling particles or walkers in the Brillouin zone and in real space, but the distribution function is obtained by changing the weights, the statistical weights that you assign to these samplers or superparticles or walkers or whatever you want to call them. And then about the Monte Carlo method, well, you know, I could talk for hours. We'll give you the gist of the model, and maybe later on I will present some results, but I would rather move to quantum transport and low dimensionality transport for the remaining lectures. So let's go in order and see how one can solve it. The method of moments. I think that historically is trying to think. To semiconductors, yes, I think is the first one. In order, as a solution of the Boltzmann equation, I think that the Monte Carlo came first, because the Monte Carlo was used during the war by the Manhattan Project for neutron transport. The transistor came at the end of the 40s, right, in 49. I think the original papers about solving the Boltzmann transport equation in semiconductors, or the so-called the semiconductor equations, came in the late 40s. So perhaps the Monte Carlo is the first one, but if you know better, let me know. I like history, so I'd be interested in knowing. So, but nevertheless, this has been the most important in the semiconductor arena. So the idea is we have to solve this messy equation. This gives us information at any given time about how many particles I have in a finite volume element, infinitely small volume element in real space and in k-space. So it's a lot of information. And you wonder whether I really need it all. Do I really need to know the full shape of the distribution functions in general? There are some situations in which you do. For example, if you want to study going back to the days of the hot electron problems, trying to think, I think it was in the 80s or early 90s, when chips in the VLSI industry had a power supply which seemed to be a constant, a physical constant of nature. It had to be 10 volts and then it became 5 volts, but they didn't want to move away from 5 volts. Devices were shrinking, the voltage was the same, so the electric fields were growing larger and larger, so electrons from going from a source to the drain gained a tremendous amount of energy. Since the VDS power supply was 5 volts, they could gain in principle up to 5 volts. So they could get injected into the gate oxide and contribute to leakage current, and more important, create damage. Hot electrons entering or even hitting the silicon-silicon dioxide interface can create damage. This can create charges that shift the threshold dynamically, and eventually your chip stops to work. So the idea was that you really need the distribution function at very high energies. You may need even its angular dependence to know how many electrons hit the interface between the semiconductor and the insulator, how many get it into the insulator, and so on. So, but this is a particularly pathological case. So you may not really need all the information that you want for the distribution function. Let me go back to here. Instead, let's do one thing. Let's consider the what in statistical, in probability theory, they're called the moments. This is a probability distribution function. If I normalize it to 1 over the entire phase space, which means what is the probability of finding a particle at position r and k in k space at time t rather than the density, so normalizing it differently, this is a probability distribution function suitably normalized. Instead of talking about the probability distribution function, I can talk about the averages or the expectation value of powers of r and k, in particular of k, over the distribution function. So I can look at the average of k times f, so the integral of k times f, the integral of f, first of all, which, okay, is equal to 1 in this normalization, is equal, integrating over k is equal to the density at position r at time t if I normalize f in such a way. The integral of k multiplied by f integrated over k will give me the average velocity or the average of flux. Remember, k is proportional to the velocity, so it will give me something proportional to the velocity. The integral over k squared, okay, k is a vector, so ki kj squared, will give me a tensor which is an energy tensor, it's proportional to the kinetic energy. The integral over k cubed will give me a third rank tensor, which is the energy flux. And I keep going on talking about the flux of the energy flux and so on. So I could, in principle, multiply this entire equation by some power of k, starting from k0, so just integrate over k the both sides of the Boltzmann equation, and see what I get. This is the first moment, or call it the 0th moment. The next moment will be multiplying by k, so I will get, for example, by integrating the time dependent of the current density equals to something, and see what I get, and I could keep going. And at each level, I will have some information. The more moments I get, the better I get. In principle, I can recover the entire information contained by the distribution function by looking at all the moments up to infinite order moment. In practice, I can stop at whatever moment is suitable for the physical goal that I have in mind. So for a long device with small electric field, I don't care about the average energy. The electron remain at thermal equilibrium. The first 2 moments, the 0 and the first, will be sufficient. For studying hot electron effects, I may need at least to have some information about the average energy that electrons gain. So we have to go to the second moment, which means the third, again, if I consider 0, 1, 2 as the first three, and so on. And I could keep going. Every time I would get a set of differential equations. So the problem now becomes a continuum model, and I would get to that. The problem is, I have it in some slide. I think I forgot to save it. But the problem is that if I do this, in principle, if I look, say, at the moment of order n, I would like to have a differential equation for the moment n, and maybe moment of order n minus 1, n minus 2, and so on, whatever I need. However, remember that dr dt is the velocity. In a parabolic band approximation, this is proportional to k. So if I multiply by some power of k, kn, and integrate this entire equation, I get at every single one of these terms will give me the nth moment. But this term here will give me the n plus 1 moment, n plus first moment. So I have a problem which is sort of similar to the problem that we had by solving by perturbation theory, the Liouville-von-Neumann equation. I never close the system. In that case, looking for a 2-particle Green's function, I ended up with a 6-particle or a 10-particle for electron-electron interaction Green's function. And I had to do something to close it. Here is the same. If I look at a differential equation for the n moment, I will have the n plus first moment to deal with. And the problem is known as the closure problem. I had to find an expression that relates whatever the n plus first moment tells me to the n moment and close it that way. And we will discuss that. Again, in the audience, there are people who are experts on this issue. So again, the moments method means, okay, I will, rather than ask for the full information given by the distribution function, I will look for the ensemble average of some physical quantity, q or t or q of k, whatever. So I take the Fourier transform of this guy, and I look at the expectation value over this probability distribution function of this quantity. Okay. Here I will normalize from now on the distribution function to the density. So the total density will be, assuming spin, I would consider spin as a separate object here. So there is a factor 2. I integrate the distribution function. This is the usual integral over k, so I have this factor 2 pi cube, which is the usual conversion factor when I go from the sum over points in k space to the integral by making it continuous. And so this will be the carrier density. So I will also assume for now that the velocity is just given to a parabolic expression. This is the group velocity, which is the gradient of the energy k dispersion, which is h bar k divided by the effective mass. So if I take the first moment, what do I get? Where am I? Here, from this term, I get just the derivative in time of the density will be equal to the divergence of the current, which is what I get from, where am I? From this expression over here. This is the velocity, and this will, if I multiply by k, I will get I can bring the gradient over here. It becomes a divergence of the velocity. This term actually cancels, because if I multiply by k, you see that this term and this term go away. You can convince yourself multiplying by k, write these two terms separately, swap k and k prime in this integration, and you find that the collisional integral gives you exactly 0. So at the first moment, I recover exactly the continuity equation, which is what we would expect, okay? And the current density is just the sort of the first moment, except for the proportionality constant h bar over n star, okay? Which I can write as the product of the electron mass times their average velocity, if I divide by 1 over f by the normalization, times the expectation value, the thermal expectation value of the velocity. So the first moment gives me just the continuity equation. The second moment, there are two different ways in which one can derive it. The first one is just a straightforward application of the moment method. So rather than multiplying by k, I actually multiply by the velocity. So h bar k over m star. And I get this expression over here, where this momentum relaxation time is expressed in this way. This is actually momentum relaxation rate, is what I get by integrating by the velocity the collisional integral. You realize that if I multiply by the velocity, I get the difference between two terms, and this is exactly what I express here. Well, I have swapped the integration over the entire k and k prime, swapping k and k prime in a second integral. So what I have is a formal definition of what is the momentum relaxation rate, which is here. So I have some expression which we'll have to manipulate a little bit to express in terms of diffusion term. This is some expression which is proportional to the field, and this is indeed the drift. And this is something that depends on the fact that the current may have some explicit dependence on time, generation recombination processes, for example. Okay, so I can rewrite it in this form. This will become a diffusion term. This will become a drift term. And this is an explicit time dependence that we may ignore, for example, in most cases. So the momentum relaxation rate or time that I have here is what comes out from the collisional integral, integrated the collisional integral. Why do I call it momentum relaxation rate? Strictly speaking, velocity relaxation rate. It's essentially, this is the scattering rate. If I take just the first integral, ignore this term, this will be the integral over all transition probabilities from k to k prime for the distribution of function k, integrated over all possible final states. But I integrate over k prime because I have two integrals over here. One is coming from the integral that I have already over here, integrating over k prime, and then I have the second integral, which is over k, that I get in taking the moment of the Boltzmann equation. So this will be essentially the integral over the entire scattering rates. As I told you, these were constants in the first moment, and indeed I get a 0. And that's why the collisional integral gave no contribution to the first moment. First, again, I apologize for the, oops. My apologies here, I lost the phosphor. Come on. Okay. So they gave no contribution to the first moment, which is the 0th moment. Again, there is this ambiguity about the numbering here. But here, what I have is, if I look at integration over k prime, what is the probability of dissipating the velocities along the ith direction, x, y, z, per unit time? So this is something which is divided by the average velocity, as I've written here, gives me the rate at which the velocity is dissipated. It makes a difference between the scattering rate and this object. The difference is due to the fact that I might have, depending on the angular distribution of the scattering probability here, this microscopic scattering probability. For example, if this is peaked for k primes which have a small angle with respect to the initial k vector, this may happen, if you remember, when I have a matrix element square that has a q dependence in the denominator, Coulomb matrix elements, electron impurity, electron-electron, scattering of electron with longitudinal optical phonons in polar material, Froelich scattering. They all have some q dependence in the denominator, which means that k and k prime differ by a small q, most likely, which means the scattering angle is small. Then in every collision, the angle of the velocity will change by a little bit. So there's not much of a dissipation of the velocity or momentum in any given collision. So the momentum relaxation rate will be much smaller, so the relaxation time much larger than the scattering time. Vice versa, if I have a matrix element which is isotropic, the same for any k prime at any angle, then this will be a total randomization of the momentum at a single collision. So the scattering rate will become equal to the relaxation rate. So this is what the major physical difference between the scattering rate and this momentum relaxation rate that I get by taking the moment with multiplying by k. So the first moment, which is the second moment in this terminology, between this relaxation rate that I get from the second moment and the scattering rate. I will also in future make a distinction between the macroscopic relaxation rates, whether it's momentum as it is here, energy as it would be later in the hydrodynamic or energy transfer model. You see that the scattering probability here is average over the distribution function. Instead, I will define occasionally microscopic relaxation rates. Notice that if I bring the VI over here, so to speak, without having average over the distribution function, I get 1 minus VI divided, K prime divided by VI of K, which is this expression. And this is the momentum relaxation rate, not average over the distribution. So we'll call it microscopic. I will make this distinction occasionally. So the first way is to multiply by K. Then I'm left with this macroscopic momentum relaxation rate. Of course, it depends on which direction I'm assuming. There's 3 of them, X, Y, Z direction. If I have a field in the X direction, we expect that the momentum relaxation rate will be different from X direction and the Y and Z on the other hand, because the electrons will be shifted in K space mainly along the X direction, thanks to the action of the field, mainly. This is not actually always true. So this is one way in which I can derive an equation for the first moment, or the second one, meaning for the current. The other approach that I can follow, rather than multiplying by this, is instead multiply by this object. This is not a guess, I mean, you know already what you want to get to. You multiply the Boltzmann transport equation by a different object by first defining this object, this momentum relaxation rate, which is neither the microscopic nor the macroscopic that I define here. Notice that I have the relaxation rate itself included in an integral. So this is actually a formal definition of tau, because it's actually tau is given by the solution of this integral equation. The reason I do that, it's because eventually we will want to obtain something that resembles a famous Kubo-Greenwood formula, and this is actually the momentum relaxation rate that you get from linearizing the Boltzmann transport equation. In this case, we multiply now not by the velocity times this object, this momentum relaxation rate. Notice that it's similar to the microscopic, I use the same symbol, but it's slightly different. And in most cases, actually, one can simplify it this way. So I multiply and I get this expression, a similar form, very similar, except that this tau now is inside the expectation value. That's the only difference, because I multiplied already by tau. And I have again something which eventually will look like a diffusion term, something that, since it's proportional to the field, I will call the drift term, because it's what the effect of the field is in accelerating the electrons and making them drift along the direction of the field, and then this term, which is the explicit time dependence. Essentially, they're identical, simply because I've defined different ways, but we will discuss it later, how to simplify this and how to extract some quantities that we can relate to other things, like the diffusion constant and the mobility out of these terms. Notice that in both cases, this equation and that equation are essentially identical. They simply differ by the way I've defined this tau. Notice that this is something which is proportional to the velocity, and yet I have a term which is proportional to the, roughly speaking, the square of the velocity here. And this is the same thing over here in this equation, right? This is proportional to v, is En times v, but here I have a v square. And this is the usual closure problem. The equation, the partial differential equation that I have in order to find what is the velocity or what is the current density, which is the same thing, actually depends on the square of the velocity, and so on. I can go on, for example, to the next moment, the third moment, which is multiplying by essentially the energy tensor. So I have 9 components here, only 6 independent, the diagonal and the 3 off diagonal because it's symmetric here. So I have 6 terms, and what I have here now is the fact that the energy, the average energy, depends on the term which is sort of a diffusion, so it's the energy flux, how energy, mainly the thermal energy, diffuses out of a given position, and then Joule heating. Electrons gain energy from the field, and you have this acceleration term. This gives you the drift current that you have. So the current here will be given by diffusion current, proportional to the density, the gradient of the electron density. So we have yet to demonstrate that this is what this term will come out. This is a drift term. This is essentially the mobility. And again, we have to see how this will come out. And then there is an explicit time dependence of the current. And here is the same thing for the energy, in which the energy per unit time in a given position changes per unit time, because energy can diffuse out very much the same way. So it's a thermal energy flux because of the drift, which is Joule heating, so the energy increases, and because energy can relax by some energy relaxation term in other ways. And this energy relaxation term now is, if you realize, is the same form that I have here. This tells me, okay, this is the probability that things happen per unit time. And this is the quantity that relaxes. What is the difference between the before and after collision velocity along the I direction, normalized by the average velocity? So it gives me the rate at which the velocity relaxes. Here I have the same thing for a given element of the energy tensor, so a k-square term. What is the difference between the before collision and after collision energy, this component of the tensor, multiplied by the probability that a transition happens per unit time, normalized by the expectation value of the energy, and integrated over all possible initial and final states. So this will be the dimension of a time, which is coming from this W. It gives me the rate at which energy relaxes. Again, for a process which is elastic, so impurity scattering. For impurity scattering, clearly the process is elastic, so the diagonal terms of the trace of this term, for example, will be 0. The energy before and after is the same. Although you may have some redistribution of the energy or the distribution function. For example, the distribution function may be accelerated along the direction of the field by this term, but it will be relaxed on perpendicular or transverse directions because of impurity collision. So the off-diagonal elements may not be 0 even in elastic processes. Okay, so one can simplify it by looking, as I just did now, considering the trace. You can look only at the trace of the average energy defined this way. This is just the ki square summed over the ijk or xyz. And then you have a simpler interpretation of this next moment equation, which is the derivative of the average energy is proportional to the diffusion of the energy out, so the energy flux, the Joule heating, how much electrons are accelerated by the field, and then an explicit relaxation of the energy. Notice again that I have the usual problem. This is the moment of the order k square, and this is a moment of the order k cube. It's a third rank tensor before tracing it out, as I wrote it over here, because I have a VI, sorry, where am I here? The EIJ, and then I have this term which will give me essentially a KL out of this term. Sorry, this term, my mistake, a DL, which is a KL. So is the usual problem of having to close it. So the problem that we will have to deal with in dealing with this is to express this term in terms of something which depends only on one velocity, And this will be clearly a relationship between the diffusion coefficient constant and the mobility. At equilibrium, this is given by Einstein's relationship, and this will be our closure. Here, the problem will be a little trickier. Again, some members of the audience have a vast experience on how to deal with this issue. I have to express this in terms of something related to this. So the third moment in terms of the second moment, and this will be the Biedermann-Franz law that typically is used, but there are some issues. And Professor Gnudi remembers conversations that we had a few years ago with IBM regarding this issue and the spurious velocity overshoot. So, in addition to this, of course, always, in all cases, we have to solve Poisson equation self-consistently. So the field that appears here is related to the density via Poisson equation. Of course, this depends also on the dopant density, whatever it is, donors, acceptors. In this case, I assume donors for a p-type, for an n-type semiconductor, but it can be anything else. Okay. Again, this is the slide that I was looking for. And again, this talks about the usual problem that we have with the closure. When I multiply by k and integrate, this is proportional to k. So I get a term coming from the diffusion piece, so to speak, that proportional to the gradient with respect to the spatial coordinates, so proportional to diffusion. I have an equation for a moment of order n that unfortunately leads me to having a term on the right-hand side, which is for the order n+1. And this is the famous closure problem. Okay, so the first model, the first is going back to this, and then, so this is just a continuity equation, conservation of charge or mass, whatever you want to call it. This is an obvious sanity check that any formulation of a problem has to satisfy. If I lose electrons at some particular point, is because they flow out of that volume around that point, and if they increase, is because they flow in, with the exception of possible generation recombination terms that appear explicitly somewhere. So, and then the second one is to look at this term, okay, which is the diffusion term and the drift term, which we can simplify in this form. How do I rewrite it? How do I, alternatively, I can formulate it this way. I can simplify this way. Well, notice that this thermal average, at thermal equilibrium, this is just the proportional to the average energy here that I have, okay, Vj squared, if I take the trace. And this term can be related at thermal equilibrium to this term. Notice that if this is a thermal equilibrium distribution function, this will be the derivative with respect to k, or the gradient with respect to k of the Fermi-Dirac distribution function, or the Boltzmann distribution function, and this is the energy, except for a kT factor. This, let's assume that it does not depend on k. Well, actually, we can, because it's, again, inside the bracket of the thermal expectation value. So this term will give me the energy times F. The terms F cancel with this 1 over F. So I have the energy times V times P. But this is proportional to the energy, again, at equilibrium. So I have exactly the same expression, a derivative with respect to J of this expression here. So I can use Einstein relation, which follows directly from that expression. And defining the mobility as whatever I define in that formula, which is this factor of E over H bar, the minus sign because we're dealing with electrons, which are negatively charged. And then the mobility is defined as the gradient within a given direction, if you wish. It's a tensor. It tells me the electrons are accelerated, or the velocity of the electrons along the I direction depends on the J direction of the field, tensorially. In an anisotropic medium, this may happen. Silicon, for example, is an anisotropic medium because the bottom of the band structure is, the equienergy surface is near the bottom of the band structure, are well approximated by ellipsoids. So this is a definition of the mobility that we will consider below. It leads to what's known as the Kubo-Greenwood formula. The diffusion constant, the tensor, diffusion tensor, is given by this object. And at equilibrium, we realize that it is the FDK, for the reason I just told you, gives me essentially a V square, an energy, a V square. So there is an immediate relationship between this and this via the only term which comes out when taking the derivative of the Dirac, of the Boltzmann expression for the distribution function at equilibrium, which is a KT, expressed in units of the electron charge. So this is the way in which essentially I get rid of the next higher order moments. This would give me, in principle, sorry, this term would need the next moment, which is the average energy. Instead, I'm assuming that the energy is the equilibrium energy, 3/2 kT in 3 dimensions, and I relate it to the mobility. Having done that, then I can write this expression, sorry, where am I here? This expression here, in terms of the current density usual expression, which is the derivative of the diffusion constant times the density, with a little caveat here, which I'll discuss in a moment, and the drift term. The drift term is quite simple. Having defined the mobilities this way, this is what I get immediately. Taking the trace, assuming that the material is isotropic, so that the mobility tensor is diagonal. This D. I remember that years ago I had a question, I forget who asked me. Maybe Bob Dutton, Professor Dutton, Stanford. Is this D inside the delta or outside? And that's a good question because unfortunately it's neither. If you go back here, you see that if I define the diffusion constant in terms of the mobility via this term, there is the tau, which is outside the gradient, but the tau is also part of the mobility. So it's also part of the diffusion constant. But this tau is outside the derivative with respect to j, index j, while the velocity square is inside. So strictly speaking, I have to make a decision here. If, as usually it happens for electron-phonon interactions, electron-phonon, I should stop there. Tau, which is the momentum relaxation time, does not depend on position, then it doesn't matter. I can bring it in because it doesn't really make any difference. If instead the tau depends on position, such as for electron impurity collisions, because that depends on a local impurity concentration, then this tau should really be outside. So if I look at what happens for electron impurity limited diffusion constant, I would have to put the D outside this expression. So it's a little tricky issue here. Okay, someone in the audience may clarify the issue better than I can. But again, it comes from this fact that I define this tau as this way, and here it looks like the derivative with respect to the spatial coordinates also acts on tau, but in the expression that I have either this expression or this one, doesn't matter, the tau is outside the derivative. So it's a little tricky issue. Okay. The mobility, by the way, if I look at this expression, I should have boxed it. This is the real definition of the mobility. Okay. So we can simplify it, assuming that the band structure is isotropic, assuming that this tau is also isotropic, it does not depend on direction, and looking at the diagonal term of the mobility only, I can simplify this integration over k as an integration of an energy, and then the mobility will be some factor in front. Notice that it's inversely proportional to the effective mass, and then it's simply the integration over the density of states, the average energy, the momentum relaxation rate at that energy, and then this is the derivative of the equilibrium distribution function over the energy. This is as a peak at the Fermi level, of course, because f of 0 is flat for small energy, in the degenerate limit is almost 1 at small energy, approaches 0 at large energy, and it's around the Fermi energy that it decays. So this is essentially proportional to a spike at the Fermi energy. It tells you that only electrons at the Fermi energy contributes to the conduction, which is not surprising. Electrons which are at much higher energy than the Fermi energy, well, there's none. So they don't contribute much simply because there's nobody there. Electrons which are deep in the Fermi sea, below the Fermi level, cannot move because of the Pauli blocking. They cannot be accelerated by the field, they cannot scatter for interactions which do not change the energy too much, so they're not too deeply inelastic, so they can scatter anywhere. It's only electrons which are in a shell of thickness kT around the Fermi level that can contribute to the mobility. And then the mobility is proportional to the momentum relaxation rate, of course. Nothing to do with the energy, it's how the momentum relaxes. And remember that the way we defined this object was looking at the change in momentum. Where is it? Here. Change in velocity, strictly speaking. It's analogous here because I'm using a parabolic band approximation, isotropic. So velocity and momentum are the same. For silicon, I have to be a little bit careful because they're not collinear. Velocity and momentum are not parallel. And then it's proportional to the density of states that I have essentially at the Fermi level. If I approximate this with a delta function at the Fermi level, which is what I get at very small temperature, then you see that it's the density of states at the Fermi energy and the momentum relaxation rate at the Fermi energy that determines the conduction. This has a name, Kubo-Greenwood formula. You may call this expression actually the Kubo-Greenwood formula. This is what we get also from linearizing the Boltzmann equation, which is essentially what we're doing here. Okay. This is, again, a repetition of what we considered before. We define a diffusion constant as the thermal average of velocity squared by taking the trace out. And we see that we can rederive the closure relationship, Einstein relationship, in a different way. This is the same thing that written in different ways that we discussed by making this equal to this at equilibrium. Remember that this relationship, this Einstein relationship, is valid only at equilibrium. And then this is again the same expression that I had before with the D either outside or inside. This is what we derive using the first method that we discussed before. This is the second method. So this is brute force integration over by K, and this instead is This instead is what we get using the second form, multiplying by the velocity times that funny microscopic momentum relaxation rate that I defined before. The same thing. So repeating again the same story. I think I'll stop here today. We have to discuss a little bit about hot electron effects. This form, either this or this, it doesn't matter. Stick to this one, no hat, simpler. This form is valid by using a closure relationship, which is okay at equilibrium. It's not okay as I move away from equilibrium. So the issue is what happens if I want to deal with a problem in which the electron energy changes significantly. So historically, this was applied to long devices. I think the first time it came by was for devices in micron channel length, several microns. The electric field were small, the electrons did not heat up significantly, so this was an excellent approximation. As device shrunk and the power supply did not, eventually they started shrinking, but still we had a period in which electrons were hot, and in short devices they can get hot much easier because the channel length is so short, comparable to the mean free path, so they can get significantly hot. By the way, this is the reason why the master equation can also apply to deal with quantum transport in a dissipative fashion in the short devices. But then we have to worry about electron heating. This expression is not valid anymore, so we will have to see what are the limitations of this drift diffusion approximation and go to the next moment. And I guess we'll continue next time. So, any question? I apologize, but after 3 hours, my throat is really, really hurting. Any question about what we've done so far? I guess that next time when we'll deal with hydrodynamic, some member of the audience will have something to say, something to contribute. And please shoot whenever you see something that requires clarification or you may wish to add anything. Okay. Yes, please. Please.
Okay. Can I ask a question about some previous slides when you talked about the random phase approximation due to random dopants, dopant position? Okay.
No, you cannot ask.
In that case,
Random dopant.
I stop here.
No, let me go there.
No, about the random dopant approximation, because okay, I met that approximation other time. I mean, in several occasions, even when we dealt with the green functions and you consider the scattering with impurities in green functions, you make this approximation of randomness of the. But I never understood that completely in devices, because it's true that impurities dopants are random in devices, but that randomness applies from device to device. I mean, if I take the same device and I study transport in one specific devices, which is one I am supposed to do after all, how can I treat the dopant as random? The position of dopant random that is fixed. I mean, dopants are not like phonons, which I can consider as random from time to time. They change, they do whatever they want essentially, but not dopants. They are in a fixed position for a given device. And the same thing applies, I mean, as far as I can see, applies to scattering with the surface roughness, because often, always, you treat the surface roughness scattering by averaging, by making some random approximation, of course. But for a given device, the roughness is not random. Okay, so how can it be that one can apply this random approximation in one specific device? That's always, so I never understood that very well.
So if you're talking about a single small device, indeed, you're absolutely right. I don't know if you remember the excitement that we saw late 80s, early 90s, I forget, when people were looking at conductance fluctuations in tiny devices, and you would trace the conductance as a function of gate bias, and there was some noise, but it was not noise. It was perfectly reproducible. You could retrace the same line back and forth many times, as long as the sample was at a fixed temperature, low fixed temperature.
Yes.
Then you would heat up the sample, cool it down again, and you would get another curve with different noise. But again, reproducible once you kept the system frozen. And the explanation was, I have a perfectly reversible, not phase randomizing fluctuations of the conductance due to scattering with impurities, which is perfectly reproducible. There's no random phase approximation here. There's no random phase cancellation. Then I change the configuration of the impurities by heating up the sample so that the impurities move around a little bit. They reshuffle, I quench it back. So now I have the same system with frozen impurities, frozen in place, but in a different configuration. And I get a random average, another random, but reproducible fluctuations. So the idea is that this was seen only in samples which are small enough. If you take a big sample, what you have is essentially the cancellation of the phases from one some sample to the next. Which is the argument that Kohn and Luttinger gave when they derived the Boltzmann equation for impurity scattering. Indeed, in a small sample, you have some phase cancellation, but not particularly strong. If the sample gets very big, then you begin to have phases coming from very many impurities, more and more as the sample size grows. And these phases now are so many that they cancel each other. If the sample is sufficiently small, then no, then you don't get this phase cancellation. The same for impurity scattering. If the device is very long, then whatever is the change of the phase that is scattering with one particular as we call it, surface step, causes at the beginning of the channel, interferes with all of the possible other scattering processes along the channel. By the time you get to the drain, all phases are cancelled out. If the device is very short and narrow, also narrow, I should add, then this doesn't happen. And in principle, I would expect that you can get some noise or some effect of the surface scattering, which is reproducible and not averaged out. So I think that it's a dimension of the sample that matters here. It gives you lots of impurities. Again, I hope it's clear. I'm not sure if you're happy.
Okay, yeah, sure.
So it's the size of the sample itself. If I add, I remember one striking example of the random phase approximation that Steve Locke showed me years ago. So we wanted to look at screening and so on, and we used the code that he wrote to use the quantum transmitting boundary method in 2 dimensions. And we looked at what is the difference between using the change of a local, so if you change the potential at one point, in principle, classically, the density changes locally, only where you change the potential. By lowering the potential at one spot, for example. Quantum mechanically, you expect a strong non-local effect. You change the potential at one point, you change the transmission probability of the waves will change all over the place. And so you expect a big difference on the density, the variation of the density induced by a change at a particular location, whether you're doing semi-classical or quantum mechanically. So he came to my office and said, look what I got. It's amazing how well the random phase approximation works. And indeed, when you add up all the waves for the electron gas that we had at some Fermi level, I forget what was the density, you add them all up. It's true. Each wave was changing completely throughout the device. When you add them all up, you add all the waves and you look at a change of the density, it was exactly the classical result. It changed only at the local place. For a sample which was sufficiently big. If the sample is made smaller, this is not true anymore. Then the waves or the density of the electrons you have, so the number of electronic states or you sum is smaller, then the phases don't cancel anymore, and then there is a difference between the classical perturbation of the density due to the change in the potential and the quantum mechanical. So again, it's related to the size of the sample that you're dealing, the number of states over which you're summing. I don't know if that helps.
Okay.
So it works remarkably well. And the thing that amazed us most was you don't need that many waves. I mean, even if you make the sample tiny so you occupy only half a dozen of states, already you begin to see a phase cancellation at places which are away from where the perturbation of the potential is. So the striking thing, really large, doesn't mean many. And that's the interesting thing. Only half a dozen or so. It's already an infinite number.
Okay.
These are, yeah, okay. So that's the answer I can give you. I hope you're happy. Otherwise, we can continue discussing. If you have counter-arguments.
Max, I have a comment.
Yes, please.
I have a comment on the equation where you have the diffusion coefficient inside the gradient operator. That
I was expecting
that was formulated by Stratton first, who investigated the situation where doping was uniform. Actually, it seems to me that the Einstein relation can be generalized in the context of the hydrodynamic model, considering as a temperature not just the lattice temperature, but the carrier temperature. So it's a sort of a generalization of the Einstein relation. And of course, in order to do that, you have to define an average temperature of the carriers related with the energy, and you have to neglect the convective term. Yeah, but after you do that, it turns out that the temperature has to be inside the gradient operator, whereas mobility, which is the multiplying factor that gives you the diffusion coefficient, should stay outside. so that if you have, for example, a gradient in doping, you don't have to take the gradient of the mobility due to the variation of doping with position. So mobility should stay outside, and instead the temperature is inside the gradient operator. This is at least what
I agree. I agree perfectly, because the mobility is this piece here.
Yeah,
It's proportional to the tau. Proportional to the tau, and the tau is outside.
The tau is outside.
So the mobility stays outside, but whatever else you have, the energy here, which is the temperature, stays inside. I agree.
Of the carriers. So
yes,
that,
indeed. So it's messy.
Okay, go ahead.
No, please, please.
No, I was saying, on the other hand, this derivative of temperature is one of the main problems of the velocity overshoot that you mentioned before. Because when you have hot electrons at the drain side of the channel that enter a region where a lot of cold electrons sit there, then the average temperature drops down very quickly. And so you have this huge velocity overshoot due to that gradient. And this is a curious effect, because of course the distribution function is far from being a Maxwellian in that case, because you have two different distribution functions, electrons coming from the channel and electrons sitting in the drain region.
You anticipate me what I will talk next time.
Oh, I'm sorry.
No, it's okay, but somewhere, indeed, I talk about the two-fluid model.
Yeah.
But actually, it's something that my former colleague Tim-Wei Tang introduced at some point somewhere. I'll find it. But actually, that's a problem that we discussed with Antonio when he was at IBM quite at length. This fake drop of temperature, which is caused by two different distributions. The hot electrons temperature doesn't change that quickly. It's simply the average between the hot and the cold electrons that make it drop so suddenly.
So this is the anomaly of the...
That's the anomaly, indeed. And I discuss it here somewhere about somewhere, the two-fluid model or whatever. But we'll talk about next time. But yes, thank you for bringing it up, because it's a major issue. And even for the drift and diffusion, so for the lowest moment, it's not, in some situations, it's not clear what to do here. Do you keep it in? Do you keep it out? You have defined D, but D is these two components, one which may depend on position and one it doesn't. So what do you do? So it's an issue.
Yeah, okay.
Okay. Any other comment? I welcome these discussions.
Good.
Okay, if not, have a good weekend.
Same to you.
And I'll talk to you next week. Bye-bye.
Bye-bye.
Bye-bye.